Hello there and welcome to the Sleepy Cosmic Lens. For astronomers in the late 20th century, part of the Milky Way felt dark, crowded, and blocked by huge clouds of dust, a region where visible light telescopes were almost useless, a region that swallowed starlight long before it reached Earth. Yet, buried inside this patch of darkness was something no one expected. A star so large it stretched every limit astronomers thought they understood. A star that makes our sun look like a spark. The future record holder for the largest star ever discovered, Stephenson 218, the discovery of a cosmic outlier. But before anyone even realized that it existed, astronomers needed a map, they needed a list, they needed a catalog. That's where an astronomer named Charles Bruce Stephenson comes in. In the 1990s, long before Stephenson 218 became a viral name in astronomy circles, Stephenson was busy doing the type of work that rarely makes headlines, building catalogs of stars. These catalogs were built so astronomers had reliable, organized lists of objects worth studying in detail. But Stephenson wasn't cataloging just any stars. He focused on red supergiants, massive stars in their final unstable phase of life, glowing bright red and losing material into space at incredible rates. They're rare, short-lived, and scattered across the galaxy. If you want to understand the violent end of giant stars, this is where you look. Stephenson's work showed groups, clusters of these red supergiants in certain regions of the sky. That alone was surprising. Red supergiants aren't supposed to clump together in large numbers. Finding more than a handful in the same neighborhood usually means one thing: a massive, very old star cluster is hiding there. And through his surveys, Stephenson identified one cluster in particular that demanded attention, a location in the constellation Scutum, a region so dusty it looked empty in visible light until infrared observations exposed the truth. This group would eventually be known as Stephenson 2, a cluster containing dozens of red supergiants, more than almost any other known cluster in the Milky Way. And somewhere inside this group, quietly glowing behind curtains of dust, sat the star that would break every size record, but at the time, no one had any idea. Stephenson had simply created the map. Stephenson 218 would be found years later. To understand why Stephenson 2 became so important, let's look at what this cluster really is. It's about 19,000 light-years away, tucked into the Milky Way's Scutum Centaurus arm, one of the galaxy's major spiral arms. If the Milky Way were a city, this arm would be one of its massive highways, full of star formation gas clouds and some of the most dramatic objects in the sky. But Stephenson 2 doesn't sit in a clean, open part of this arm. It sits behind a wall of interstellar dust, the kind that blocks visible light almost completely. To a normal telescope, this region looks like a dark patch with nothing interesting going on. That illusion is dangerous. It makes astronomers underestimate what's hidden in these regions. But infrared observations, light that passes through dust much more easily, tell a different story. When infrared maps of this patch of sky were made, something shocking appeared: a huge, bright, dense cluster, one of the most massive known open clusters in the Milky Way, a cluster containing over 25 red supergiants when most clusters don't even have one. To put that in perspective, finding a single red supergiant in a star cluster is rare. Finding 2 or 3 is astonishing. Stephenson 2 has more than 25 making it one of the largest collections of massive dying stars in our galaxy. Think of them as giant glowing warning signs, telling astronomers massive stars lived here, massive stars died here, more will die soon, and the biggest, brightest, most extreme of them all was Stephenson. But again, at first this was just a cluster, a catalog entry, a list of dots on a page. The true size of the star inside it wouldn't be understood until astronomers revisited the region with better instruments, better data, and a better understanding of how to remove the effects of dust. In the early 90s, astronomy looked different back then. Digital imaging was still developing. Infrared astronomy was powerful, but limited compared to what we have now. But Stephenson's goal was clear: track down and classify luminous red stars in regions where other astronomers had overlooked them. His surveys involved scanning crowded fields of stars, identifying strong infrared sources, isolating objects with colors typical of red supergiants, and organizing them into detailed catalogs. These catalogs didn't just include coordinates, they included brightness measurements, approximate spectral types, and notes about how obscured or reddened each object appeared. This mattered because dust doesn't just block light, it also changes light, making stars appear redder and dimmer than they truly are. Stephenson recognized this region of the Milky Way was flooded with dust, and that meant one thing: use infrared or see nothing. This approach immediately revealed stars no one had noticed before. Some were bright, some were incredibly bright, and some were so bright they didn't fit the usual pattern. One of these unusual entries was a star that would eventually get the label Stephenson, but in the early surveys it didn't stand out as the largest star ever found. It simply stood out as strange. Too bright through dust, too red, too luminous for what early models predicted. A star that didn't quite match the others. An outlier. And outliers are always where discoveries begin. To understand why Stephenson's work mattered so much, imagine watching a fire through thick smoke. From far away, the smoke blocks most of the light. You might only see a faint glow, even if the fire is huge. That's exactly what interstellar dust, visible light, gets scattered and infrared light passes through more easily. This difference is everything. If you tried to observe Stephenson 2.0 with a traditional optical telescope, you'd think it was faint or unremarkable. The dust makes it look far weaker than it is, but switch to infrared. Suddenly, you're looking at one of the brightest and largest stars in the entire Milky Way. Infrared surveys allowed astronomers to pierce heavy dust clouds, uncover hidden red supergiants, measure brightness without losing most of the light, estimate temperature using more reliable wavelengths, and gather enough data to classify the stars properly. Without infrared, Stephenson 2.0 would still be hiding today. The dust around the cluster dims visible light by several magnitudes. That's like lowering a stadium floodlight to the brightness of a candle just by putting enough dust between you and the bulb. Infrared astronomy didn't just help, it made the entire discovery possible. When the stars in Stephenson 2 were first classified, astronomers weren't trying to find the largest star ever discovered. They were simply studying a cluster filled with evolved massive stars. But during these early classifications, something unusual happened. Several stars in the cluster were extremely large and extremely luminous, much larger than typical red supergiants. Some of them were potential hypergiants, a category reserved for the biggest, brightest, most unstable stars known. Stephenson 2.18 showed signs of being on the extreme edge of this group. But the data wasn't yet precise enough. What astronomers did notice, even early on, was its brightness through dust was unusually strong. Spectral data placed it in the very late M-type range, around M6, cooler and more extended than typical supergiants. Its estimated luminosity after dust correction was enormous. It was physically too large for the standard size predictions at the time. Still, no one was comfortable calling it the largest star yet. The uncertainties in distance, dust, and luminosity were too large, but the star refused to blend in. Every new observation hinted that it wasn't just another red supergiant in the cluster. It was something far more extreme, and then came the key moment: better dust models, plus more accurate distance data and modern infrared measurement. When all three pieces came together, the real size of Stephenson 218 finally became clear, and it shattered the scale. Let's pause and rehook with a quick scale comparison, because this is where Stephenson 218 stops being interesting and becomes absurd. If you dropped it into our solar system, Mercury, Venus, Earth, and Mars are all gone. Jupiter is inside it, and Saturn is also inside it comfortably. Its radius is so massive it reaches beyond the orbit of Saturn. And this isn't an exaggeration, it's the real, observationally supported size. No other known star in the Milky Way reaches farther. But again, none of this was obvious when Stephenson made his catalogs. It took decades of follow-up work, new instruments, and deeper analysis of this dusty region to reveal what the original surveys hinted at. And this brings us back to the Milky Way. It hit its largest star behind dust. Stephenson built a map. Infrared astronomers exposed the hidden cluster. Spectroscopists gathered the temperature data. Dust correction models improved. Gaia refined the distance. Modern infrared surveys locked in the luminosity. And only then, only after stacking layer after layer of evidence, did astronomers realize the monster they had uncovered. A star that dwarfs every other known star in size. A red hypergiant at the edge of stellar physics. A cosmic outlier that defies the scale we're used to. Stephenson 218 wasn't just another entry in a catalog. It reveals the Milky Way is still hiding giants we're not prepared for. One of the most interesting things about the discovery of Stephenson 218 is how ordinary it looked at first. There was no dramatic first detection, no headline, no moment when astronomers gasped and realized what they were seeing. Instead, the truth came together slowly, like solving a puzzle. First, identify unusually bright red stars. Then, notice they belong to a massive cluster. Next, correct the dust that hides most of their light. After that, refine their distances. Finally, calculate actual luminosities and sizes. When this final step was done accurately for Stephenson 218, astronomers saw the real number, a radius around 2,050 to 2,500 times that of the Sun. That's not just big, that's record-breaking. And the star instantly became the largest star ever measured with credible data. Not because someone pointed a telescope and saw it right away, but because decades of surveys, catalogs, and infrared mapping slowly exposed the truth, hiding behind layers of dust. The breakthrough observation. In a region filled with red supergiants, brightness alone does not make a star special. These stars are naturally luminous. They glow fiercely because their outer layers are pushed outward by powerful radiation from deep inside, creating huge extended atmospheres that make them look bloated when compared to smaller stars like the Sun. But even within a cluster of giants, there are limits. There are predictable patterns in how bright a red supergiant can appear based on its temperature and distance. There are relationships between luminosity and size that help astronomers determine whether a star is behaving normally for its evolutionary state. The troublesome star inside Stephenson 2 did not respect any of those boundaries. Astronomers first took a closer look because its infrared output was extreme, even after accounting for the heavy dust between the star and Earth. The raw brightness values alone were oddly elevated, but once corrections for extinction were applied, the star's luminosity soared to a level that no one had expected. When a star sits behind thick dust, the majority of its visible light is erased long before it reaches a telescope. That means the infrared brightness often becomes the most trustworthy measurement because longer wavelengths cut through dust more effectively. If the infrared readings are strong even before dust correction, then the star behind that cloud is producing a staggering amount of energy. The early steps of the analysis involved confirming that the extreme infrared brightness was coming from a single source. Crowded star fields in the Milky Way's inner regions can overlap. Stars that appear to be one object can sometimes be multiple stars crowded together in the line of sight, but follow-up observations with higher resolution ruled out that possibility. The data were not contaminated. The brightness was real. One star was producing levels of radiation that did not match the rest of the cluster. At this point, the question shifted from whether the reading was accurate to what type of star could possibly be responsible for those values. Red supergiants can vary in size, but even the largest known examples rarely cross certain theoretical boundaries. Their temperatures, usually in the range of 3,000 to 4,000 Kelvin, determine how large they can appear at a given luminosity. When astronomers combined the temperature estimates for this star with its corrected luminosity, they began to get radius measurements that stretched far beyond the typical values. The earliest radius estimates placed the star at well over 1,000 times the size of the Sun, and later refinements pushed that number even higher. This was when researchers started to question whether they were still looking at a typical red supergiant or something more extreme. The term hypergiant is not used casually in astronomy. It is reserved for stars that sit at the edge of stability, stars with such powerful internal processes that they shed material at phenomenal rates and often display highly irregular surfaces. Hypergiants are extremely rare. They burn through their fuel quickly and live dangerously short lives. For a star to be upgraded from supergiant to hypergiant, its luminosity, mass loss rate, variability, and spectral characteristics all need to point to a level of instability that goes beyond normal red supergiant behavior. The strange star inside Stephenson 2 had not yet been fully classified as a hypergiant, but several aspects of its data were leaning in that direction. Its apparent magnitude in the infrared was too strong. Its luminosity was too high, even after conservative dust corrections. Its temperature, though low compared to smaller stars, matched the profile of a very late-type red supergiant whose outer atmosphere was extremely extended. Its spectrum suggested a swollen, unstable atmosphere filled with molecules typical of the coolest and largest evolved stars. All of these signs implied that the star did not sit comfortably within the usual supergiant range. This was the moment when astronomers began treating the object as something more than just another red star in a crowded cluster. The term anomalous started appearing more often in the note. Researchers examining its spectral type classified it around M6, which placed it among the coolest and most extended known supergiants. The cooler a red supergiant is, the more physically enormous it becomes, because cooler temperatures mean the star's surface must spread outward to radiate the same amount of energy. When the luminosity of this star was combined with a temperature near this range, the implied radius was colossal. The earliest calculations underestimated the true scale because distance estimates were still uncertain and extinction corrections were still conservative. Even with these uncertainties, the star's radius was estimated to be at least 2,000 times the radius of the Sun. That alone would have made it one of the largest stars ever discovered at the time. But as astronomers refined the cluster's distance and improved the dust modeling, the star's radius continued to grow. Once newer infrared data were used, along with updated extinction laws and more accurate parallax information from Gaia, the star's radius extended into a range that no other known star could match. Its final accepted radius placed it firmly beyond the orbit of Saturn if it were placed at the center of our solar system. The breakthrough came when astronomers compared its luminosity with the rest of the cluster. Stars in a cluster form around the same time from the same material. They follow predictable evolutionary paths based on their mass. That means they should exhibit consistent relationships in brightness and temperature for each evolutionary stage. The mysterious star was too bright for its position on these. It stuck out like a flare in the data, sitting above the usual parameters for red supergiants. It had the luminosity of a hypergiant, yet it existed in a cluster where most stars were already oversun. The fact that it still managed to exceed even those giants made it clear that it was not just an outlier, but an extreme outlier. Astronomers revisited the photometric data repeatedly, testing alternative explanations. If the star were actually closer to us than the rest of the cluster, its brightness would seem higher than it truly was. If it had an unusual composition, its colors might differ from expectations, but every attempt to explain away the anomaly failed. Its position in the sky matched the cluster, its motion matched the cluster, its extinction matched the cluster, its infrared signature matched the cluster. Everything pointed to it being a genuine member of Stephenson. That meant the extreme luminosity was real, not the result of an observational trick. One of the biggest uncertainties for any star shrouded in dust is how much of its light is being absorbed or scattered. If astronomers underestimate the dust, the calculated luminosity will be too small. If they overestimate the dust, the luminosity will be too large. When the dust correction for this star was refined, the luminosity consistently rose to a level that placed it among the most radiantly powerful stars in the Milky Way. Using those luminosity values in the temperature range from spectroscopy, the radius calculation grew to values that exceeded known hypergiants like VY Canis Majoris and UY Scuti, stars that had previously been thought to represent the upper boundary of how large a single star could become. The moment astronomers realized these measurements were stable and not artifacts of poor dust modeling was the moment the star transitioned from being a curiosity to a breakthrough object. It was no longer just a giant. It was the giant. The extreme brightness in the infrared was not just a feature, it was a clue pointing directly toward its enormous size, and the fact that this brightness persisted even after sophisticated corrections made it clear that this star sat in a class of its own. The breakthrough observation did not happen in a single night. It unfolded through layers of confirmation. The photometric anomalies were the beginning. Anomalies by themselves do not create scientific revolutions, but they demand further investigation as each new piece of evidence reinforced the previous one. The star's identity, as the largest known star, became stronger. It was a process built on consistency. Every new measurement, every new dust model, Every new distance refinement pointed toward the same conclusion. This star was an extreme hypergiant, whose size surpassed every recorded example. One detail that added confidence to the analysis was the temperature stability derived from its spectral type. A star this large must be extremely cool at its surface because a star's luminosity depends on both its temperature and its radius. A hot star does not need to be large to be bright. A cool star must be enormous to produce the same amount of energy. The spectrum of Stephenson 2-18 placed it securely in the cool, late type range. Combining cool temperatures with extreme luminosity left no other explanation. A cool star cannot appear that bright unless it is insanely large. The physics of stellar atmospheres leaves no alternative option. Even though astronomers were careful not to rush into calling it the largest star, the numbers kept repeating themselves across independent studies. By the time multiple teams had confirmed the extinction values and distance estimates, the radius was no longer a tentative measurement, but a robust one. The star was simply too luminous and too cool to be anything other than a red hypergiant with a radius far beyond any ordinary stellar size. The first suspicions that it might be a hypergiant came not from size calculations, but from its behavior as seen in its spectral features. Hypergiants often display signs of massive stellar winds and unstable atmospheres. Their outer layers do not hold together calmly. They drift outward in dense flows, sometimes creating circumstellar envelopes or shells. Stephenson 2-18 showed hints of this instability in the molecular lines present in its spectrum. These signs were not enough to classify it definitively at first, but they served as early warnings that the star's equilibrium was delicate. The early luminosity calculations pushed the star's power output to more than 400,000 times the luminosity of the Sun. That number alone indicated that the star was nearing the theoretical upper limit for how large a red hypergiant can become before its outer layers become too unstable to maintain a structured atmosphere. Astronomers knew that once a star reaches this threshold, it is destined to collapse in a spectacular supernova. The star's enormous luminosity placed it near this line, reinforcing the idea that its size was not just large, but truly extreme. The more the data was studied, the more the stars seemed to challenge the boundaries of theoretical models. Stellar evolution models predict that red hypergiants should reach large sizes, but they also suggest a soft upper limit because gravity and radiation pressure must balance in a delicate equilibrium. If a star grows too large, the outer layers become so diffuse that the star begins shedding mass heavily. Stephenson 2-18 was operating close to this threshold, which made astronomers question whether its size represented the physical maximum that a star can achieve before it becomes unstable to the point of collapse. Initially, older infrared surveys could detect its overwhelming energy output, but they couldn't cut through the layers of interstellar dust with enough precision to reveal the star's actual size and temperature. The star that would later be famous as Stephenson 2-13 was still hiding in the noise. Everything about it seemed oversized, but that uncertainty hung over every estimate. No astronomer was going to declare the largest star ever found on rough values alone. To settle the matter, researchers needed newer tools, telescopes able to resolve tiny details even in a region where dust dims most wavelengths. They needed clean spectra, precise distances, accurate dust corrections, and high-fidelity light measurements. Only then could they pin down the temperature, luminosity, and radius with confidence. And that's exactly what the coming decade of technology gave them. The real confirmation didn't come from a single dramatic discovery night. It was a steady tightening of constraints, each pass removing another layer of uncertainty. It started with detailed spectroscopy, because knowing a star's spectral type isn't just a label, it tells you the physics of its surface, the energy it emits per square meter, and the expected position it should occupy on established stellar evolution tracks. And for this one, spectroscopy was essential because all signs pointed toward it being one of the coolest and largest kinds of evolved massive stars ever documented. When astronomers first targeted this object with high-resolution spectrographs, they already knew it displayed elements of a very luminous red supergiant. But the spectrum they retrieved made the classification. The absorption lines characteristic of a late-type star were deep and well-defined, revealing a surface temperature far below that of ordinary red giants. Its spectrum aligned with the signatures of an M-class supergiant, specifically M6, an extremely late and extremely cool subclass. This classification alone pushed the star deep into hypergiant territory. There simply aren't many stable configurations that allow a star that cool to maintain that level of brightness without being enormous. While that single label, M6, may look simple on paper, the physics behind it carries enormous weight. It points to a surface temperature far lower than the sun, yet, even at that low temperature, the star was radiating energy at a level that shouldn't have been possible unless its surface area was enormous. And surface area's radius. The colder the star, the larger it must be to produce its observed luminosity. The spectral type effectively set the temperature scale, and once the temperature was nailed down, astronomers could calculate luminosity with far greater accuracy. But they still had another wall to break through. This region of the Milky Way isn't just dim, it distorts starlight heavily, reddening it and scattering it so much that early brightness measurements were completely buried under false signals. Without correcting for dust absorption and scattering, the star could be misclassified by orders of magnitude. That problem had haunted earlier radius estimates, but modern methods now allowed for detailed reddening corrections using multi-band photometry and extinction models built specifically for this area of the galaxy. Astronomers began by analyzing how the star's light stretched across near-infrared wavelengths. These wavelengths can bypass dust more effectively, but they're still influenced by comparing the observed color of the star to what an M6 supergiant should look like without dust. They could calculate exactly how much interstellar material was altering the signal. Once those corrections were applied, the star's true luminosity jumped dramatically. Instead of being merely bright for a red supergiant, it was now revealed to be one of the most luminous, cool stars ever recorded in the Milky Way. That dramatic luminosity increase after dust correction immediately pushed the radius estimate into record-breaking territory. But there was another critical step. For luminosity to be accurate, distance has to be right. A star that looks bright could either be intrinsically luminous or simply closer than expected. Earlier catalogs relied on the assumption that the star was a true member of the Stephenson 2 cluster, which placed it roughly 18,000 light-years away. That was a reasonable assumption, but not a confirmed measurement. Then Gaia came into the picture. Gaia's mission is to measure stellar positions, distances, and motions with unprecedented precision. And even though it struggles with extremely bright or extremely reddened stars, it still offered valuable data for this region. Its measurements helped refine the distance to the Stephenson 2 cluster and confirmed that this star was not a foreground object masquerading as a monster. It was indeed located at the cluster's distance. No tricks, no misleading projections, no conveniently close luminous red giant contaminating the data, with Gaia narrowing the distance range. Astronomers could plug the corrected distance into their luminosity calculations with confidence. Now the numbers were solid, with temperature confirmed through spectroscopy, luminosity corrected for dust, and distance refined by Gaia. Astronomers could finally calculate the star's physical radius using the Stefan-Boltzmann relation, and that calculation delivered the number that cemented the star's place in record books, a radius somewhere between 2,150 and 2,000. That translates to a swollen, unstable sphere of plasma so large it stretches beyond the orbit of Jupiter, and depending on the exact value, possibly into the orbital region where Saturn travels. Even the low end of that radius range makes it the largest star ever reliably measured. And because this isn't a theoretical radius based on poorly constrained assumptions, but one grounded in a full chain of high-precision observational steps, the scientific community took it seriously. Spectroscopy set the temperature scale, dust corrections exposed the true luminosity, Gaia pinned down the distance. And all of these steps combined forced the radius solutions into the same extreme range. It was no longer a star that looked enormous only because dust played tricks or because it was misclassified. Every independent measurement pointed toward the same conclusion. To get a sense of how extraordinary this radius is, it helps to consider what it means for a star to even reach such dimensions in the first place. Most massive stars shed enormous amounts of mass as they evolve, preventing them from expanding indefinitely. Their outer layers become unstable, and strong stellar winds strip material away before the star can grow beyond a certain point. That natural limit is why most well-studied red supergiants, for example, Betelgeuse, stay within a radius range of several hundred to perhaps 1,000 solar radii. Breaking past that requires conditions rare enough that astronomers usually hesitate before accepting such a measurement. Stephenson 218 doesn't simply break that limit, it multiplies it, and because of how tightly the observations now constrain its temperature and luminosity, any attempt to shrink its radius would contradict the spectroscopy, the dust modeling, or the Gaia distance. The parameters lock together. They leave no wiggle room for the star to be anything smaller. The radius remains gigantic, no matter how conservative the assumptions. This final confirmation shifted the entire discussion from speculation to certainty. Astronomers now had a star that wasn't simply large for its type. It was redefining the upper boundaries of what a massive, evolved star in the Milky Way could reach. It forced researchers to revisit models of late-stage stellar evolution, mass loss, and the internal physics of hypergiants. Because a star this size isn't merely oversized, it's unstable by nature, held together only temporarily, sitting at a point in its life where every change in temperature, rotation, or mass loss could push it toward collapse. But before researchers could explore that phase, they needed one last check: consistency across different observational methods. When independent teams examined the star using different telescopes, different dust maps, and different modeling techniques, they all arrived at the same general radius range. Every approach confirmed that the star dwarfs nearly every known red supergiant. Only a handful of theoretical stars from simulations of extreme late-stage evolution even approach this size, and none have come with observational certainty. Stephenson 218 therefore stands alone, not just as a large star, but as the largest confirmed star currently known. The confirmation phase also highlighted why this star remained so obscure for so long. Most record-breaking celestial objects draw massive attention immediately after discovery. But this one was hidden behind layers of dust, wrapped in conditions that make precise observation difficult, and located in a complex region filled with overlapping light sources. The early catalogs treated it as just one of many infrared bright supergiants. Only when modern instruments provided clarity did the true scale emerge, and that clarity didn't just make the case stronger, it exposed the limitations of earlier assumptions about what hypergiants can achieve in their final stages. Stars like this don't quietly fade away. They grow volatile, unpredictable, and physically extreme. They lose mass at staggering rates, pushing their envelopes outward while their internal structure becomes less stable. And because of its immense radius, Stephenson 218 radiates energy from an enormous surface area even at its low temperature. That means its luminosity is thousands of times greater than the sun's, even though each square meter emits far less energy than the sun's surface. The star is so swollen that gravity at the outer layers is almost negligible, allowing matter to drift outward in slow but steady winds. This continual shedding of material creates a faint surrounding haze, a kind of extended atmosphere that makes the star appear even larger at certain wavelengths. Modern telescopes can detect the spectral signatures of these extended layers, confirming mass loss that aligns with what such a massive cool star should exhibit at this stage. These layers complicate modeling because they blur the boundary between the star's surface and its surrounding material. But even when accounting for this haze, the central photosphere, the actual visible surface, still falls within the record-breaking radius range. Dust, haze, and mass loss may influence details, but they don't shrink the star into anything less than a titan. With the radius confirmed, astronomers could also reevaluate the star's mass. Hypergiants at this stage often have far lower masses than their luminosity suggests, because they've shed much of their original material. So while Stephenson 218 may have begun life with more than 40 solar masses, it's likely far lighter today. That mismatch between mass and radius adds to its instability. It is essentially a giant, inflated shell supported by ongoing energy production deep inside, but stretched nearly to the limits of what a star can maintain without breaking apart. This is where modern telescopes reveal more than just size. They provide insight into the star's internal physics. High-resolution spectra show strong molecular absorption features, confirming the cool temperature, but also revealing turbulent motions in its atmosphere. The outer layers shift, rise, and fall over time, producing slight variations in brightness that are typical of hypergiants near the end of their life cycle. These fluctuations aren't random. They're signs of the star struggling to maintain equilibrium. None of these features take away from the radius measurement. They strengthen it, because only a star in such an extreme, evolutionary state would display that combination of temperature, luminosity, instability, and mass loss. The observational evidence aligns from every angle. This is the final picture modern telescopes delivered. A massive star cooled to the point where its outer layers have expanded beyond almost every known limit, situated deep within a cluster that itself is a cradle of massive stellar evolution. It is a hypergiant not just in title, but in every measurable physical property. Stephenson 218 is now the benchmark by which candidates for largest star are evaluated, and because the observational chain spectroscopy, dust correction, Gaia distance, luminosity modeling forms a fully consistent picture, it stands as one of the most reliable measurements of an extreme stellar object in our galaxy. No other known star currently surpasses it with equal certainty. Canopy of a red hypergiant. A red hypergiant isn't just a larger version of a red supergiant. It sits in a category that astronomers treat with caution because stars in this state break the normal rules of stability. They are so swollen, so luminous, and losing so much mass that they barely hold themselves together. Only a handful of confirmed red hypergiants exist in the entire Milky Way, and each one represents a brief and violent stage near the end of a massive star's life. Stephenson 218 fits directly into this classification, and to understand its scale, its instability, and its future, it helps to understand what defines a hypergiant at the most basic level. The key difference between a red supergiant and a red hypergiant is not simply size. Many supergiants grow extremely large, but they maintain a degree of internal balance that allows them to exist in that inflated state for a longer period. Hypergiants, on the other hand, cross a threshold where their internal pressure, outer layers, and mass loss behavior becomes so extreme that stability turns temporary. They are not comfortable stars. They are stars operating at the upper edge of what physics allows. Astronomers define a red supergiant as a massive star that has exhausted hydrogen in its core and expanded dramatically as it fuses heavier elements. Its surface temperature typically falls between 3,500 and 4,500 Kelvin, giving it a cooler, reddish appearance. Its radius may grow to several hundred times that of the Sun, and in rare cases over 1,000 times. These stars are huge, bright, and impressive, but they are still bound by a level of structural order. A red hypergiant steps beyond that. Its luminosity rises so high that its outer layers are barely held down by gravity. The energy flowing outward from the core pushes on the material in the envelope with such intensity that it can lift entire shells of gas away from the star. Hypergiants shed mass far faster than supergiants, sometimes millions of times faster than the Sun loses mass. This extreme mass loss becomes one of the main identifiers of hypergiant status. If a red supergiant is like a giant balloon, inflated to the point of strain, a red hypergiant is one that has already started leaking gas from every direction. Temperature plays a key role in understanding this difference. Red hypergiants are among the coolest massive stars known, with surface temperatures often around 30,200 Kelvin, sometimes even lower. A temperature this low means that each square meter of the star's surface emits less energy than the surface of hotter stars, which might initially sound like a weakness, but the opposite is true. To shine as brightly as it does with such a cool surface, a red hypergiant must expand its outer layers to an enormous size, compensating for the low energy flux by increasing its surface area. The lower temperature is a sign that the star has expanded so far that its outer layers are stretched thin, cooling as they move outward. This bloated, low-temperature envelope creates a dangerous condition. When a star swells to that degree, the force binding its surface weakens dramatically. Gravity becomes weaker at larger radii, while the outward pressure from the intense energy flow remains strong. This imbalance pushes the star into a zone where even slight fluctuations can throw material into space. The outer layers no longer behave like a tightly controlled structure. They move, shift, and sometimes detach completely. Hypergiants also show complex spectra that reveal extended atmospheres, molecules forming in cool layers far from the core, and turbulent motions that indicate a lack of stable equilibrium. Their surfaces aren't smooth or uniform. They bubble, expand, and contract as pockets of gas rise and fall. These motions originate from the chaotic interactions between convection, radiation pressure, and gravity. The result is a star that looks steady from afar, but is constantly changing when viewed with detailed instruments. Instability is the hallmark of a red hypergiant, and that instability comes from multiple layers of physical stress building simultaneously. Deep inside, the core is burning heavier elements in rapid succession. As the star burns through its fuel, the balance between gravity pulling inward and radiation pressure pushing outward becomes harder to maintain. With every shift in nuclear burning, the envelope responds, expanding or contracting in unpredictable waves. These expansions can stretch the outer layers even further, lowering the surface gravity and making mass loss even easier. Hypergiants sit so close to the Eddington limit, a point where radiation pressure overwhelms gravity, that they are effectively in a constant tug of war. The Eddington limit is a theoretical threshold that defines how bright a star can be before its own light becomes strong enough to blow away its outer layers. Hypergiants hover near this limit, meaning their luminosity is practically at the maximum value that their mass can support. When a star approaches this point, the outer layers become unstable and begin to drift away. This is why hypergiants shed mass so aggressively. Mass loss rates provide one of the most important clues about hypergiants. While the sun loses material at a slow rate through a gentle solar wind, hypergiants lose matter at rates millions of times higher. They produce dense, slow-moving winds driven by the star's intense radiation and its unstable envelope. These winds carry away gas and dust, forming huge extended envelopes around the star. In some cases, these envelopes grow so large that they resemble miniature nebulae surrounding the star, filled with material that was once part of its surface. These extended envelopes aren't just a side effect, they are a defining feature. They create a thick, cooler region around the star that interacts with the surrounding interstellar medium. This envelope often absorbs and re-emits radiation, making the star appear even brighter in infrared wavelength. The presence of these dusty or gaseous layers also provides direct observational evidence of the star's instability. They show that the star has been shedding mass for a long time and continues to do so at a rate far beyond what ordinary supergiants exhibit. Stellar winds are another critical component. When astronomers talk about winds from hypergiants, they aren't describing a gentle solar-like outflow. These winds can move at tens or hundreds of kilometers per second, pushing material outward in all directions. The speed and density of these winds reflect the internal struggles of the star. Strong winds mean strong radiation pressure and weak surface gravity, which usually points toward a hypergiant classification. The winds also contribute to creating shock regions where material collides, heats up, and cools again as it flows outward. This interaction between layers of material creates a chaotic environment that surrounds the star and often appears as an extended halo when viewed through sensitive instruments. Some of the most complex circumstellar structures ever documented come from hypergiants because these stars don't lose mass smoothly. They eject material in pulses, arcs, and irregular waves, depending on what is happening deep inside the envelope. Because hypergiants change so rapidly, their luminosity can shift noticeably over relatively short periods. These changes aren't massive enough to confuse them with variable stars, but they indicate instability in the outer layers. The brightness variations often come from changes in temperature, convection patterns, or the creation of dusty shells. When a new dust shell forms, the star may briefly appear dimmer in visible light, but brighter in infrared wavelength, because dust absorbs visible light and re-emits it as heat. These dust shells themselves are indicators of violent events. A stable star does not create sudden outflows of dust. Only a star losing mass at extreme rates can produce these thick layers that drift outward and cool. When astronomers detect multiple shells at different distances from the star, they know it has been shedding material in repeated episodes over thousands of years. Each shell marks a moment when the star's envelope briefly destabilized and released a large amount of mass. A hypergiant's envelope is so extended that it cannot be thought of as a single, well-defined surface. Instead, it is a series of layers, each one less tightly bound than the one beneath it. The density decreases with distance, and because the temperature is low, molecules can form in the outer layers. These molecules create specific absorption lines in the spectrum, which astronomers use to track velocities and motions within the envelope. When they see broad, complex absorption features, they know the gas is moving in many directions at once, a classic sign of instability. One of the most important consequences of this instability is that hypergiants have extremely short lifetimes. Once a star enters this phase, it does not remain here for long. A hypergiant may only survive in this state for tens of thousands of years, an incredibly brief moment compared to the millions of years it spent as a stable, massive star. The rapid mass loss eventually strips the envelope, changing the star's structure so dramatically that its evolutionary path shifts. In many cases, a hypergiant will transition into a hotter, more compact phase as it prepares for its final explosive end. Because hypergiants are so unstable, they often have lower masses than their enormous radii suggest. As they shed material, they lose mass much faster than they lose luminosity. This creates the unusual situation where a star with a relatively low mass can still shine with extraordinary brightness simply because its envelope remains massive and extended. This mismatch between mass and luminosity is one of the clearest signs that a star has moved into the hypergiant regime. Everything about a hypergiant points toward a system under stress. Its atmosphere is stretched, its gravity weakened, its winds fierce, and its envelope full of motion. The low surface temperature, around 3,200 Kelvin, is not a sign of calm. It's a sign the star has expanded to a point where its outer material is barely hanging on. A temperature this low in such a luminous star can only exist when the radius has grown to an extreme size. A red hypergiant represents the final expansion phase of a massive star before it collapses or transitions into a hotter stage. Its physical characteristics. Stephenson 218 is not just large, it is a star that forces astronomers to rethink what large even means. Its numbers stop being numbers and become scales that most people never encounter in everyday life. Talking about its physical characteristics requires stepping past ordinary stellar comparisons and entering a zone where objects behave differently simply because their size changes the physics around them. A star this big does not act like the sun, it does not look like the sun, and it certainly does not hold itself together the way smaller stars do. Everything about its structure, brightness, density, and rotation reflects the extreme conditions inside and around this record-breaking giant. The first physical characteristic that stands out is its radius. Depending on the method used, Stephenson 218 is estimated to be between 2,150 and 2,500 times the radius of the Sun. A radius this large is not just a matter of scale, it defines how the entire star behaves. If Stephenson 218 were placed where the Sun sits now, its outer layers would extend past Jupiter's orbit and approach Saturn's orbital distance. In other words, everything from Mercury to Jupiter, including Earth, would be deep inside its swollen envelope. The Earth would not orbit around the star. It would exist inside material drifting through the star's extended atmosphere, with temperatures and pressures far beyond what any solid planet could endure. To understand this size on a more structural level, take the Sun's radius, roughly 700,000 kilometers, and multiply it more than 2,000 times. Stephenson 2 to the 18's radius reaches billions of kilometers. Its diameter is so large that light, the fastest thing in the universe, would take hours to travel from one side of the star to the other. This already places it beyond the scale of nearly all other known red supergiants. Even massive stars like Betelgeuse and Y Canis Majoris, both famous for their enormous size, fall short by a wide margin. Where those stars push toward the upper end of supergiant radii, Stephenson 2 to the 18 surpasses them by such a large amount that it required astronomers to recheck their calculations multiple times before accepting the result. But size alone does not describe the full story. The next defining physical characteristic is its luminosity, roughly 440,000 times the luminosity of the Sun. A number like that only becomes meaningful when considering what it truly represents. Luminosity is the total energy a star releases every second. The Sun emits an enormous amount of energy, enough to sustain every climate system, weather pattern, and biological process on Earth. Stephenson 218 emits hundreds of thousands of times more energy every second, and it does so while having a much lower surface temperature. That is possible because its surface area is vastly larger. The energy from its core spreads across an area so huge that the temperature drops to around 3200 Kelvin. But the total energy flux remains enormous. A luminosity this high also tells astronomers something about the star's internal processes. A star does not shine at that level unless its core is burning fuel at an extreme rate. The core must sustain reactions that release massive amounts of energy, enough to support the weight of its oversized envelope. A star this bright is living fast. It burns through each stage of nuclear fuel rapidly, which is why stars of this type do not survive long. Luminosity also determines how strong the outward radiation pressure is. And in a hypergiant, that pressure plays a major role in shaping the star's outer layers and driving mass loss. Another crucial physical characteristic is the density of its outer layers. Despite its colossal size, Stephenson 218 is not a heavy, compact object. In fact, its outer regions are astonishingly diffuse. The surface layers of the Sun are already not dense by everyday standards, but Stephenson 218 extends this thinness to an extreme degree. The material in the outer envelope is so spread out that it is closer to a high-altitude atmospheric density than anything resembling a solid surface. Astronomers sometimes describe hypergiants by saying their outer layers are as thin as vacuum by human standards. And this is not an exaggeration. The outer envelope is so extended and so weakly held by gravity that atoms drift in slow, chaotic motions rather than forming any stable structure. This low density has several important consequences. First, it makes the star extremely unstable. A dense star can resist changes in pressure or temperature more effectively because its matter is tightly packed. Stephenson 218, however, has an envelope where most of the mass is concentrated closer to the center, and the outer layers consist of gas spread across volumes so large that they barely feel the gravitational pull from the core. A tiny shift in internal pressure can push entire regions of material outward, causing the envelope to fluctuate in size, shape, and density over short periods. Second, the low density is why the star's surface temperature remains so low. The material in the envelope is so spread out that it cools easily. Even though the core produces immense energy, by the time that energy reaches the surface, it is radiating through a very large extended region, losing heat along the way. The star's cool appearance is not a sign of weakness. It is a direct result of its oversized, diffuse atmosphere. Third, the extremely low density makes mass loss inevitable. When matter is barely held to the star by gravity, even a moderate amount of radiation pressure can push it away. And in the case of Stephenson 218, radiation pressure is far from moderate. Combined with convection and instability within the envelope, the star constantly sheds material into space. The density is so low that the distinction between the surface of the star and the regions above it becomes blurred. There is no clear boundary. Instead, there is a gradual transition from the star's extended atmosphere into the surrounding space, with particles drifting away in a slow, steady flow. Another physical characteristic worth highlighting is its rotation. Massive stars tend to begin their lives rotating rapidly, but as they evolve, their rotation slows due to the expansion of their outer layers and the conservation of angular momentum. When a star expands to hypergiant proportions, its rotation slows dramatically. Stephenson 218 rotates far more slowly than it did when it was a compact young star. Its large radius spreads out any rotational velocity across a much larger circumference, reducing the surface rotational speed to extremely low levels. Even though the star rotates slowly, rotation still affects the shape of the envelope. The star may not be a perfect sphere. The extended atmosphere can bulge slightly around the equator due to even the small amount of centrifugal force generated by rotation. This effect is mild compared to the bulging seen in faster rotating stars, but it is still present. Slow rotation also contributes to the stability of the inner regions. A fast rotating hypergiant would lose material even more violently, so the slow rotation actually prevents even greater mass loss. Rotation also affects how convection behaves in the envelope. Convection cells in a hypergiant can be enormous, far larger than those on the Sun. They move heat from the core to the surface in a pattern influenced by rotation. In a star with faster rotation, these cells would align in bands or more organized patterns, similar to the Sun's granulation. In a hypergiant like Stephenson 218, slow rotation combined with its enormous radius allows convection to form massive, irregular cells. These rising and falling columns of gas can span huge regions of the outer envelope, contributing to surface variability, changes in brightness, and sudden pulses of mass loss. The slow rotation also interacts with the phenomenon of expansion. The star is not static. Its envelope expands and contracts unevenly as convection, radiation pressure, and internal nuclear processes shift over time. This expansion is not dramatic enough to make the star fluctuate in radius constantly by factors of 2 or 3, but it does move in measurable ways. When astronomers track the star over time, they find that its outer layers drift slightly outward or inward, depending on the conditions inside the star. This constant movement contributes to the creation of shells of material around the star. Each expansion phase can push out a new layer of gas, while each contraction phase allows gravity to pull the envelope slightly tighter before the next wave of expansion. Another feature that helps define Stephenson 218's physical character is the enormous volume it occupies. Volume increases with the cube of the radius. While the radius is around 2,000 times larger than the Sun's, its volume is several billion times larger. This is another way in which the star defies everyday intuition. Its mass is much larger than the Sun's, but not billions of times larger. Its mass may only be around 20 to 30 times that of the Sun, depending on which model is used. This means the envelope is spread across such a huge volume that it becomes extremely dilute. Most of the star's mass is not in the outer layers, but closer to the core, where nuclear fusion occurs. This mismatch between volume and mass plays a role in nearly every physical characteristic of the star, from its cool temperature to its instability. It also explains why the star's gravitational pull weakens dramatically at the outer edges. The core may be massive, but gravity decreases with distance. At billions of kilometers from the center, the gravitational pull weakens enough that the outer layers can escape easily. The outer envelope is essentially a cloud of loosely bound gas, rather than a solid or even semi-solid surface. Another way to understand its structure is through the concept of escape velocity. At the Sun's surface, the escape velocity is high enough that particles need significant energy to break free from the star's pull. But at the surface of Stephenson 218, the escape velocity is much lower because gravity is weaker at such large distances from the core. When radiation pressure pushes upward, it easily overcomes the weakened gravity, which is why mass loss becomes such a dominant process in hypergiant. The star's high luminosity also feeds into its physical behavior in another important way. It drives strong stellar winds. These winds carry away gas and dust, shaping the extended envelope. The winds are not fast compared to those of hotter stars, but they are extremely dense because of the large amount of material lifted off the surface. This means Stephenson 218 feeds the surrounding space with a steady flow of matter that will eventually contribute to new stars or contribute to the chemistry of the interstellar medium. Another characteristic worth noting is how the star's brightness is distributed across different wavelengths. Because of its low surface temperature, the star emits most of its energy in the infrared part of the spectrum. That means it appears brighter in infrared observations than in visible light. This is why infrared astronomy was crucial in its discovery. But here, this detail helps explain the physical behavior of the star. Its infrared brightness reflects the coolness and size of the envelope. A smaller star with the same temperature would be far dimmer, and a hotter star would emit more energy in visible light. Stephenson 218's energy is spread across such a wide surface that infrared wavelength dominate. The physical characteristics of Stephenson 218 also influence how the star interacts with its environment. Its extended envelope fills a wide region of space, and the material leaving the star forms a kind of moving boundary between the hypergiant and the surrounding interstellar medium. This boundary can create shock fronts where the stellar winds collide with surrounding gas. These shocks heat the material and then cool as the gas flows outward, forming complex structures that astronomers can detect. Even though the star is enormous, its gravitational influence does not extend indefinitely. The region where its gravity dominates is limited by how quickly mass is lost and how low the surface gravity becomes. As the envelope expands farther into space, the star's ability to hold on to the material weakens, and it eventually merges into the surrounding medium. This creates a gradient rather than a sharp edge, which is another characteristic of hypergiant. Stephenson 218 so demonstrates the relationship between temperature and radius in extreme stars. A star cannot grow to such a large radius unless its internal processes push outward strongly enough to inflate the envelope, and the envelope cannot remain inflated unless the core provides enough energy to prevent collapse. But because the temperature is low, the star must expand to maintain its luminosity. If the radius was smaller, the star would have to be hotter to shine as brightly as it does. Instead, the star takes the opposite route. It expands to a massive radius, lowering the surface temperature while keeping the luminosity high. Life expectancy of Stephenson 218. When astronomers talk about Stephenson 218, they rarely talk about it as a typical massive star because nothing about it falls under the category of typical. Even among the red hypergiants, which already sit in the extreme upper end of stellar evolution, Stephenson 218 stands far past the boundary line. Its size, luminosity, and instability point to one unavoidable conclusion: this star is old for its kind, burning through the last stages of its life and entering the period where everything inside it becomes chaotic, uneven, and dangerously unstable. To understand what that means, it helps to look at the age of the cluster it belongs to, what type of nuclear burning it is currently going through, how its outer layers behave, and why such gigantic stars burn out much faster than smaller stars like the Sun. The Stephenson 2 cluster is estimated to be between 14 and 20 million years old. Astronomers determine the age of a cluster by studying the stars inside it and identifying which ones have already left the main sequence, which ones are still on it, and which ones have moved into later stages like red supergiants. In this cluster, many stars have already evolved into red supergiants, which gives astronomers confidence in this age range. That might sound young, but for massive stars, 20 million years is already late in life. A star with this much mass burns through its fuel so quickly that it simply cannot last as long as lower mass stars. The Sun, for example, will live for around 10 billion years. Stephenson 218, despite being far more powerful and far more luminous, will not last even a tiny fraction of that. A few tens of millions of years is all a hypergiant gets, and Stephenson 218 is already deep in the final phases of that short lifespan. Determining where exactly it sits in its evolutionary timeline comes down to understanding what kind of nuclear reactions are occurring in its core. A star's life is defined by what it burns. And when a star reaches a certain size and mass, the sequence of reactions happens quickly and violently. A hypergiant begins with hydrogen fusion in its core, just like any other star, but it burns through that hydrogen far faster than a smaller star. Once the hydrogen supply is exhausted in the core, the star contracts slightly. Its temperature rises, and helium fusion begins. That marks the beginning of the red supergiant phase. By the time Stephenson 218 reached its current enormous size, it had already gone through that transition. Helium fusion does not last long for a star of this mass. And once helium begins to run out, these stars move to carbon fusion and other heavier element reactions that require even higher temperatures and pressures. Most evidence points to Stephenson 218 being at the end of helium burning or transitioning into carbon burning. This conclusion is based on several factors: its extreme radius, its low surface center, its instability, and its association with the cluster's age. A star swells dramatically when helium is exhausted, and the expansion becomes even more pronounced during carbon burning. Its radius of more than 2,000 times the radius of the Sun is consistent with these late evolutionary stages. Its internal structure at this point is layered like an onion, hydrogen burning in shells around a helium shell, helium fusing in deeper layers, and possibly carbon starting to fuse even closer to the core. These layers burn at different speeds, creating pressure imbalances that affect the star's surface. Once a star reaches this point, everything inside it becomes unpredictable. The core contracts as fuel runs low, the outer layers expand, then contract, then expand again, and those cycles can happen on timescales of months or years. This is why hypergiants develop such large convection cells, giant rising and sinking pockets of hot plasma that can stretch across enormous sections of the star's surface. These cells are far larger than anything the sun produces. In the sun, convection cells are roughly the size of continents or countries. In a hypergiant, a single convection cell can be larger than the orbit of. These cells create chaotic brightness changes, irregular surface motions, and huge outflows of material. One of the clearest signs of internal chaos is pulsation. Stephenson 218 does not pulsate like a neatly timed variable star with predictable beats. Its pulsations are irregular, driven by the imbalance between pressure from fusion and the pull of gravity. When the core contracts, it heats up, fusion increases, and the outer layers swell. When the outer layers expand too far, they cool, fusion drops slightly, gravity gains the upper hand, and the star contracts again. Each of these movements shifts the star's brightness and surface temperature. None of it is controlled. None of it is stable. These cycles are the kind of behavior astronomers expect to see in a star at the edge of its life. The outermost layers of Stephenson 218 are barely held to the star by gravity. Its surface gravity is extremely low because the star is so large. The mass is still enormous, but that mass is spread across such a gigantic radius that the gravitational pull at the surface is weak. As a result, the star loses mass at a staggering rate. Hypergiants shed matter through powerful stellar winds that blow outward from the star in every direction. These winds can carry off enough material to completely reshape the star over time. In some hypergiants, these winds have carved out huge shells or clouds of gas surrounding the star. Many red hypergiants in our galaxy sit inside extended envelopes made of dust, molecules, and lost plasma. These envelopes form when the winds cool and condense as they move away from the star. The instability that drives mass loss in Stephenson 218 is tied to the conditions inside the star. When a star becomes this large and cool on the surface, it develops a region where radiation pressure pushes outward with enormous force. Radiation pressure comes from the photons produced by fusion in the core. As those photons move outward, they collide with particles in the star's outer layers, pushing them away from the core. In a hypergiant, the radiation pressure can become so strong that gravity no longer holds the outer layers in place. The result is a slow but steady peeling away of the outer envelope. Some stars lose several Earth masses of material each year. Although the exact mass loss rate for Stephenson 218 is difficult to measure due to its heavy dust environment, even with uncertainties, astronomers agree that the mass loss is massive and continue. Large convection cells contribute to this mass loss by lifting material from deep inside the star and carrying it upward until it reaches regions where the gas cools, condenses into dust, and becomes part of the outflow. This cycle can remove huge amounts of material from the star in a short time. The dust then absorbs and scatters light coming from the star, altering the star's observed brightness and spectrum. That makes it difficult to determine the star's properties from Earth. but it also confirms how unusually unstable the star is. A stable supergiant does not lose mass this violently. A star entering the end of its life, hypergiants of this type also develop strong turbulence in their atmospheres. The layers are not smooth, even, or calm. Instead, they shift unpredictably, creating hot spots and cool spots that alter the star's appearance. Some regions rise and fall like colossal waves. Others collapse inward or erupt outward, releasing bursts of gas. Over time, these surface changes create temporary structures in the star's surrounding envelope. None of these patterns last long because the star changes too quickly. Astronomers can measure the effects of these surface movements in the shifting spectral lines of the star. When one region moves away from Earth, the spectral lines shift one direction. When another region moves toward Earth, they shift the opposite direction. Stephenson 218 shows the kind of spectral irregularities expected from a star whose surface behaves like a boiling, unstable sea of plasma. All of this chaos is rooted in how fast massive stars burn through their nuclear fuel. Unlike the Sun, which sips hydrogen slowly, a hypergiant consumes fuel at an enormous rate. The Sun converts around 600 million tons of hydrogen into helium every second, which sounds huge, but compared to a hypergiant, it is tiny. A star like Stephenson 218 burns through its hydrogen millions of times faster. That is why it became a supergiant in a fraction of the time the Sun will spend on the main sequence. Once helium fusion begins, the pace accelerates even more. Each successive stage in the burning process takes less time than the last. Hydrogen burning lasts most of a star's life. Helium burning lasts just a fraction of that. Carbon burning is even shorter. The stages after carbon, oxygen, neon, silicon happen so fast that they take place on timescales of centuries, years, or even days in the most massive stars. While Stephenson 218 may not have reached those very last stages yet, it is certainly close to the boundary where its remaining lifetime is measured in tens of thousands of years, not millions. For a human civilization, that seems unimaginably long. For a star, it is the blink of an eye. The final stages move too rapidly and violently for the outer layers to respond smoothly. The star expands, contracts, heats up, cools down, and storms erupt across its surface as the internal energy output changes. All of these are signs that the star is preparing to shed even more mass and eventually collapse. Hypergiants also suffer from what astronomers call opacity-driven instability. In certain temperature regions inside the star, the gas becomes more opaque, trapping radiation temporarily. When enough radiation gets trapped, pressure builds up, forces a portion of the layer outward, and then the gas becomes less opaque again, allowing radiation to escape. This results in a cycle of event and contraction inside the star that eventually destabilizes the outer layers. The deeper layers experience this instability repeatedly as the fusion shells evolve. Another contributing factor is the enormous size of the star's convective zone. In stars like the Sun, convection occurs only in the outer layers. In hypergiants, convection zones can extend much deeper. Convection brings hot material from the interior to the surface and sends cooler material inward, which causes rapid changes in brightness. In Stephenson 218, the convective motions are so large that they create bright and dark patches across the surface that can last for years. These patches shift unpredictably, creating fluctuations that astronomers observe as irregular variations in the star's light. The mass loss that comes from these instabilities plays a major role in determining how much time the star has left. When a star loses mass, it changes the balance between gravity and internal pressure. If radiation pressure becomes too strong relative to gravity, mass loss accelerates even more. This runaway process can strip away significant amounts of material before the final collapse. In some hypergiants, this process creates spectacular nebulae around the star. Although the heavy dust surrounding Stephenson 218 makes it difficult to observe any large-scale structures around it directly, still the presence of infrared excess, meaning the star emits more infrared light than expected, shows that dust is present and being heated by the star's radiation, confirming that the star is surrounded by a significant envelope of material. Its turbulent atmosphere and heavy mass loss confirm that the star is rapidly approaching a final stage of evolution. Once the core accumulates enough iron, it can no longer produce energy through fusion. Iron fusion consumes energy instead of producing it. So when iron builds up in the core, it marks a point of no return. The core collapses under its own weight, temperatures rise catastrophically, and the outer layers are blown away in a supernova. Massive stars like Stephenson 218 almost always end their lives this way. The exact details, whether it becomes a Type 2 supernova, whether the core forms a black hole or a neutron star, depend on how much mass the star retains at the moment of collapse. Given the extreme mass loss in hypergiants, there is a chance that Stephenson 218 might lose enough mass to produce a supernova that leaves behind a neutron star. But many astronomers think a black hole is more likely. A star this large, even after shedding enormous amounts of material, will probably still retain enough mass in the core to collapse into a black hole. The violent collapse and explosion would likely illuminate the surrounding dust cloud, creating a temporary bright nebula. Whether or not it produces a long gamma-ray burst is uncertain, as those are usually associated with rapidly rotating stars stripped of their outer layers. But the collapse will certainly release enormous energy. Even though Stephenson 218 sits thousands of light years away from Earth, the eventual explosion would be visible from our planet as a bright point of light, likely visible with the naked eye for weeks or months. But that event will not happen anytime soon on human time scales. Tens of thousands of years remain a realistic estimate. In cosmic terms, though, it is very close to the end. Stephenson 218's remaining life can be compared to a giant engine running hotter and harder than it was ever designed to. Every reaction in its core happens under extreme conditions, and each step burns fuel faster than the one before. All that internal pressure keeps pushing outward, stretching the star's outer layers farther than gravity in support. The result is the strange, unstable giant we see, enormous, bright, fragile, and constantly losing material. Its days as a stable star ended long ago. Now it exists in a state dominated by instability. The convection cells tear through the surface, mass streams into space, temperatures shift wildly across different layers, and the core moves rapidly from one burning stage to the next. A star with this level of internal chaos simply cannot survive long. Every indicator, its radius, its luminosity, its instability, its cluster age, aligns with a star nearing its final evolutionary phase. Stephenson 218 will not fade quietly. Massive stars end violently, and this hypergiant fits every requirement for a spectacular death. Whether it collapses into a black hole or briefly shows one of the brightest supernovae the Milky Way has seen in ages, the physics guiding its fate is already in motion. The fusion reactions in its core are approaching the final steps. The outer layers are leaking into space. The internal chaos is escalating. Everything points toward an end that has been inevitable since the day the star formed. The Stephenson 2 cluster. Stephenson 218 is extraordinary on its own, but no star exists in isolation, and its environment explains why an object this massive and unstable could even form in the first place. To understand this hypergiant, you have to look at the cluster it belongs to. Stephenson 2, one of the most important and extreme stellar groups in the Milky Way. Located nearly 19,000 light-years from Earth along the Scutum Centaurus arm, this cluster is buried behind heavy dust, crowded with massive dying stars, and shaped by a violent star-forming past. It is not a quiet neighborhood. It is a region built for short-lived giants, a place where huge stars ignite, race through their lives, and move toward collapse far faster than normal stars. Stephenson 2 is known for containing the largest confirmed collection of red supergiants anywhere in the Milky Way. There is no other cluster that holds this many huge, swollen, late-stage stars in one location. That fact alone tells astronomers a lot about its history. Red supergiants only appear in large numbers when a region forms massive stars at the same time. These stars then evolve quickly through their lives and reach the red supergiant phase almost together. When you see dozens of them packed tightly inside a single cluster, it means the entire cluster formed from a concentrated burst of star formation, producing stars with many tens of solar masses all at once. And because massive stars have such short lives, the presence of this many red supergiants signals that the cluster must be young. Young in cosmic terms, but old for the stars inside. The fact that a cluster like this even exists is unusual. Most clusters do not create such a high number of massive stars. They produce a mix of low-mass stars, some medium ones, and only a few massive ones. Stephenson 2 is different. It produced a remarkable number of high-mass stars, almost simultaneously. That single feature sets it apart and turns it into a giant laboratory for studying the final stages of stellar light. With so many red supergiants and hypergiants in one region, astronomers can track how these stars behave, how rapidly they burn their fuel, and how they respond to their own internal instability. To understand how Stephenson 2 formed, you have to look at where it sits within the galaxy. The Scutum Centaurus arm is one of the Milky Way's major spiral arms, packed with dense molecular clouds, dust lanes, and regions where star formation has been extremely active. This specific area is known for producing massive clusters, some of the largest and most heavily obscured in the entire galaxy. Stephenson 2 is part of a larger complex of clusters, groups, and star-forming remnants that trace the shape of the arm. Because this region is so rich in dust and cold gas, it has all the raw material needed to build stars with enormous mass. But the same dust and cold gas that allow massive stars to form also hide them from view. Dust lanes block visible light so effectively that the cluster is almost completely invisible in typical optical wavelengths. When astronomers point ordinary telescopes at this region, they see a dark patch with faint hints of starlight leaking through. But most of the stars, including the giant ones, are hidden behind thick clouds. This is why Stephenson 2 remained poorly understood. For decades, it was only visible in wavelength that could punch through dust, and before the rise of modern infrared surveys, those wavelengths were much harder to use for detailed studies. This made infrared astronomy crucial for uncovering the true nature of this cluster, Infrared light travels through dust much more easily than visible light, allowing astronomers to see deep into the cluster and identify stars that were completely invisible in optical observations. When early infrared catalogs and surveys began mapping the Milky Way's obscured regions in the late 20th century, Stephenson 2 finally appeared not as a small group of faint points, but as a dense cluster of extremely bright, extremely red stars. That discovery changed how astronomers viewed the entire scutum region and confirmed that this part of the galaxy was packed with clusters that had previously gone unnoticed. Stephenson 2 turned out to be one of the most important of these clusters because of its population of red supergiants. The presence of so many giant stars tells astronomers that the cluster must be massive in total mass, not just in individual stars. You cannot form dozens of red supergiants unless the original cluster had a vast number of massive stars, because only a small percentage of stars ever grow that large. This means Stephenson 2 likely began as a cluster containing hundreds of thousands of solar masses of material, enough to produce a long list of high-mass stars that would later evolve into the objects we see today. High-mass stars evolve quickly because their cores burn through hydrogen at an incredible rate. A star with 10 times the mass of the Sun can burn through hydrogen 1,000 times faster. A star with 20 or 30 solar masses burns even faster. That is why the cluster's red supergiants are such valuable markers. They reveal the age of the cluster without needing to rely on more uncertain methods. When you see so many red supergiants at the same time, you know the cluster must be young enough for all those stars to survive, but old enough for them to reach this late phase of evolution. Astronomers estimate that Stephenson 2 is between 14 and 20 million years. That might sound like a wide range, but it is precise enough for understanding the cluster's evolution. Within that time frame, all the massive stars born in the cluster would have already left the main sequence and expanded into red supergiants. The most massive ones would have evolved even further, possibly reaching hypergiant phases like Stephenson. This means the cluster is currently in a rare transitional period where almost every giant star is nearing the end of its life. This concentration of doomed giants is not normal. Most clusters lose their massive stars quickly because those stars explode early in their lives, often before the cluster becomes easily observable. Stephenson 2 seems to be caught at the perfect moment, late enough for nearly every massive star to have swollen into a red supergiant, but not so late that most of them have exploded yet. This is why astronomers sometimes call it a factory of doomed giants. It is a region that built enormous stars rapidly, aged them quickly, and placed them on a synchronized path toward collapse. The cluster does not just contain one failing giant. It contains dozens that will all reach their endpoints in a relatively short span of cosmic time. To understand how this cluster came to exist in this unusual state, you have to look at the star-forming history of the region. The Scutum Centaurus arm has undergone multiple waves of star formation triggered by the shock fronts that sweep through spiral arms as they rotate around the galaxy. These shock fronts compress gas clouds, causing them to collapse and form stars. In regions with enough dense material, star formation happens on a huge scale. A single collapsing molecular cloud can form a cluster containing thousands of stars. If the cloud is massive enough, it can produce many high-mass stars at once, which is exactly what seems to have happened with Stephenson. The region around the cluster shows evidence of older clusters and remnants of earlier star-forming events. Some of these older clusters may have exploded in supernovae that further compressed nearby gas, igniting new waves of star formation. The shock waves from these explosions move outward, sweeping through molecular clouds and triggering rapid, intense star formation. This chain reaction can produce clusters like Stephenson 2, which form dozens of high-mass stars almost simultaneously. But this intense star-forming history also creates an environment full of dust and heavy elements because supernovae release so much material into the surrounding space. Over time, the region becomes heavily obscured. The dust blocks visible light so effectively that the entire environment disappears behind a thick veil when viewed through traditional telescopes. This is why Stephenson 2 remained hidden for so long. Visible light astronomy simply could not see through the dust lanes between Earth and the cluster. Infrared astronomy changed everything. When infrared detectors became sensitive enough to map deep regions of the Milky Way, astronomers began to see through the dust. They discovered not just isolated stars, but entire clusters, some of them enormous, sitting in regions previously believed to be empty. Stephenson 2 appeared in these surveys as a dense concentration of exceptionally bright infrared sources, each corresponding to a red supergiant. These stars glowed strongly in infrared because their cool surfaces emit radiation at those wavelengths, and because the dust absorbing their light re-emits it in the infrared as well. Without infrared astronomy, Stephenson 218 might never have been identified, because the cluster as a whole would have remained a dim, obscured patch on star charts. Even modern optical telescopes cannot penetrate the dust in this region. Only near-infrared and mid-infrared observations reveal the cluster's true structure and stellar population. Instruments like the 2-micron All-Sky Survey 2MASS, later mid-infrared space missions, and ground-based infrared spectroscopy made it possible to classify the stars inside the cluster and measure their properties precisely. This is also why Stephenson 2 and similar clusters are so valuable to astronomers. They allow scientists to study massive stars in late evolutionary stages without needing to wait for rare individual examples to appear in isolated regions. Clusters like this one provide a snapshot of how giant stars evolve in groups, how they influence each other, and how their collective winds and radiation shape the surrounding medium. The location of the cluster in the Scotum region also means it sits near some of the most active and crowded star-forming structures in the Milky Way. The Scotum Centaurus arm is home to several giant molecular clouds, large OB associations, and multiple red supergiant-rich clusters. Stephenson 2 is part of a larger complex often referred to as the Scotum red supergiant clusters. These include several massive clusters, all hidden by dust, all containing unusually high numbers of red supergiants. This entire complex represents one of the most important environments for understanding how massive stars evolve, interact, and reshape galaxies. And yet, even with all this context, Stephenson 2 stands out. Its combination of size, number of supergiants, and extreme stellar population is unmatched. Within that environment, Stephenson 218 emerges not just as another star, but as the most extreme member of a group already filled with extremes. Its size, luminosity, instability, and evolutionary stage makes sense only because it formed in a region capable of producing such giants in the first place. The cluster around it continues to evolve as well. The stars within Stephenson 2 are ejecting material into space through their stellar winds, creating a turbulent environment filled with gas and dust. Over time, these winds will mix with the cluster's remaining material, possibly triggering new regions of star formation or altering the dynamics of the surrounding interstellar medium. When the first wave of supergiants goes supernova, the shock waves will reshape the cluster even further. Some of the lower mass stars may survive these explosions, while the higher mass stars will collapse into neutron stars or black holes. Even now, the dust surrounding the cluster continues to play an important role in observation. Because visible light is so strongly absorbed, astronomers must rely on infrared to continue studying the cluster's evolution. These IR observations allow scientists to monitor the brightness changes of individual red supergiants, track their mass loss, measure their temperatures, and estimate their distances more accurately. Without infrared data, the entire cluster would be reduced to a dim silhouette, hiding all of its structure and behavior. What makes Stephenson 2 even more important is that it shows how common or uncommon clusters like this really. Before the rise of modern IR astronomy, astronomers underestimated how many massive clusters existed in the inner Milky Way. Stephenson 2 and its neighboring clusters revealed that the galaxy has been producing huge clusters far more frequently than once believed. These clusters contain many of the galaxy's most massive stars, but they are invisible in optical light because of the heavy dust lanes that fill the inner galactic plane. Only IR surveys expose their true number. Stephenson 2 is therefore a bridge between what the Milky Way appears to be in visible light and what it truly is. In visible wavelengths, the inner galaxy looks dark, patchy, and empty in many regions. But when you remove the dust through infrared observation, the same regions erupt into brightness, filled with clusters, massive stars, and complex structures of gas and dust. Stephenson 2 is one of the clearest examples of how misleading visible light can be in dust-heavy regions. Its position in the Scutum Centaurus arm also places it in one of the galaxy's most dynamic environments, shaped by spiral density waves. These waves compress clouds, ignite star formation, and influence cluster movement. As the galaxy rotates, Stephenson 2 slowly moves along its orbit, drifting inward from where it originally formed. Over the next tens of millions of years, the cluster will continue drifting and slowly dispersing as individual stars escape through gravitational interactions and as supernova blasts reshape the cluster's structure. Even though the cluster will not remain bound forever, its influence will persist. The remnants of massive stars, neutron stars, black holes, and expanding supernova shells will continue shaping the region long after the cluster has dissolved. But for now, Stephenson 2 is in its prime as a concentrated population of massive late-stage stars, each one nearing the end of its life cycle. This environment explains why Stephenson 218 reached such an enormous. It was born in a region capable of producing a massive star, surrounded by neighbors on similar evolutionary paths. It evolved quickly, expanded dramatically, and now sits as the largest known star in a cluster defined by extreme. Without this environment, a star like Stephenson 218 would be far less likely to exist. The local interstellar medium near Stephenson 2 shows complex structural patterns created by earlier generations of massive stars that ended their lives with core collapse explosions. These explosions can carve cavities dozens of light years across. When the shock fronts expand into the surrounding gas, they push material outward in sweeping arcs. After thousands of years, the shock slows, but the cavity remains, and its interior stays filled with hot plasma that gradually cools. Over hundreds of thousands of years, This cavity becomes a low-density pocket surrounded by thicker regions of gas. If multiple supernovae occur in roughly the same area, the resulting cavities overlap, distort one another, and create a stacked structure rather than a simple sphere. Observations suggest that the Stephenson 2 region likely sits near such overlapping remnants. Into this already reshaped medium came winds from the red supergiants, born in the same cluster as Stephenson 2.18. These winds travel much more slowly than supernova shockwaves, but over long periods, they become significant. A typical red supergiant may lose mass at a rate of 1/10,000th to 100,000th of a solar mass per year. It sounds small, but stretched over hundreds of thousands of years, it becomes substantial. The material they shed includes molecules, dust grains, and heavy elements that were cooked inside their interiors. These outflows join with the leftover debris from older explosions, enriching the region and feeding the next generation of star-forming clouds. Because there are so many red supergiants in the Stephenson 2 cluster, their winds overlap and merge. This creates a shared envelope of slower-moving material that fills the cluster's volume. Even though the space between the stars is enormous from a human perspective, it's crowded in astrophysical terms. Each star contributes to the density and composition of this shared medium. Where these winds collide, they create small compression fronts. Over time, the winds collectively build up a cloud that envelops the cluster in a diffuse yet chemically enriched environment. Among these stars, Stephenson 2.18 stands out because hypergiants tend to lose mass even more aggressively than typical red supergiants. Although Stephenson 2.18 does not currently show a confirmed nebula around it, hypergiants usually create extended envelopes that can grow to many times the radius of the star itself. These envelopes form because the star's outer layers are so loosely held that material slips away and drifts outward. If Stephenson 2.18 had been observed at a slightly different stage, it might have possessed a detectable nebular halo, but its current state likely represents an ongoing mass loss lays without a concentrated shell. The material it sheds blends directly into the surrounding medium rather than forming a neat, glowing bubble. The lack of a visible nebula around Stephenson 2.18 is not unusual for its environment. The region contains so much dust and so many overlapping winds from nearby giants that individual shells are often diluted. Material that would otherwise form a distinct nebular layer is quickly mixed with the cluster's shared envelope. If the star were alone in a quieter region, its outflows might sculpt a more recognizable structure. But inside Stephenson 2, everything overlaps. Despite the lack of an identifiable nebula, astronomers still study the way hypergiants like Stephenson 2.18 sculpt their local medium. When a hypergiant releases material, the outflows expand slowly. These winds are dense but sluggish, moving at tens of kilometers per second instead of the thousands of kilometers associated with younger, hotter stars. Because the winds move slowly, they pile up in layers, compressing nearby gas and altering the structure of molecular clouds. In a cluster with many massive stars, these overlapping influences help to define the region's density patterns. Gravity then acts on these patterns, pulling denser pockets inward until they collapse and form new stars. Even in the late stages of their lives, red hypergiants still influence the next generation of stellar birth. The combination of winds and old supernova-shaped cavities also affects how radiation moves through the region. Dust grains absorb ultraviolet and visible light, warming up and re-emitting the energy as infrared radiation. This means that even though the region is dark in optical wavelengths, it shines brightly in infrared surveys. Astronomers use this infrared glow to map the thickness of dust and to study how the cluster interacts with its surrounding medium. The level of extinction in the direction of Stephenson 2 is among the highest in the Milky Way, which explains why visible observations failed to reveal anything. Without infrared telescopes, clusters like this would remain hidden behind the galaxy's dusty curtain. The presence of many red supergiants also creates a unique chemical environment. These stars contribute heavy elements such as oxygen, silicon, magnesium, and carbon to the space around them. As these elements mix into the local medium, they become part of future generations of stars and planets. The region around Stephenson 2 is therefore not only turbulent, but also rich in the building blocks needed for future planetary systems. The Milky Way's spiral arms depend on this enrichment to sustain long-term star formation. Massive stars live short lives, but they supply the materials necessary for the formation of rocky planets, complex molecules, and dense molecular clouds. The local environment is further shaped by radiation pressure from younger massive stars located near the cluster. Blue and white stars in the broader Scutum Centaurus arm emit strong ultraviolet radiation that influences dust grains and gas pockets even at great distances. This radiation can push dust outward, heat the edges of old cavities, and help maintain the temperature of the surrounding region. Although Stephenson 218 is far cooler than these young stars, it still sits in a neighborhood dominated by their influence. How we know its size. A star's radius does not come from stretching a ruler across its surface. It comes from the light it releases, how bright it appears from Earth, and how that brightness changes after accounting for distance and dust. Stephenson 218 sits in one of the most dust-choked regions of the Milky Way, buried behind layers of obscuring material that dim and distort its light long before it reaches our telescopes. That means the star's true brightness is not what we see. It must be reconstructed mathematically, but reconstruction only works if astronomers know exactly where the star is. This is why distance is the foundation of the entire measurement. If a star is far away, it must release more energy to appear as bright as it does from Earth. If the same star is closer, its true luminosity is lower, since radius is tied directly to luminosity and temperature. Even a small mistake in distance can inflate or shrink the radius dramatically. Stephenson 218's radius is so extreme that early estimates were met with skepticism, not because astronomers doubted the physics, but because they were unsure if the underlying distance was right. Gaia DR2, Data Release 2, and later DR3 provided the most precise mapping of star positions and motions the Milky Way has ever seen. Instead of estimating distances through comparisons or indirect modeling, Gaia directly measures the tiny shifts in a star's position as Earth orbits the Sun, a method known as parallax. The technique is simple in concept. The star wobbles slightly against the background as Earth moves, and the size of that wobble reveals the star's distance. For nearby stars, the wobble is large enough to measure easily. For distant stars, it becomes extremely small. Stephenson 218 is so far away that its parallax is barely detectable, buried in noise, and affected heavily by dust. But even small, noisy measurements from Gaia improved the overall cluster estimate, because astronomers could average data from hundreds of member stars. With Gaia DR2 and DR3, cluster distances sharpened. The updated measurements aligned closely with the earlier no 6 kiloparsec estimate, but tightened the error margins, reducing the uncertainty enough to firm up the luminosity calculations for the cluster's red supergiants. That meant astronomers could take the brightness they recorded from Stephenson 218, corrected for dust, adjusted for the updated distance, and calculate its true luminosity with much greater confidence. Once luminosity is known, the star's radius can be derived through basic physics. Every object that emits heat radiates energy, according to equations describing black body radiation. Black body radiation isn't a theory reserved for astrophysics. It applies to anything that emits thermal energy, from iron heated in a furnace to planets warming under their suns. The hotter an object is, the more energy it emits, and the peak of that emission shifts toward shorter wavelengths. Stars act like giant black bodies, each with its own characteristic temperature and brightness curve. Stephenson 218 emits most of its energy at infrared wavelength because its surface temperature is low by stellar standards, hovering around 3. That temperature places it firmly in the red hypergiant category, where the energy output comes from a bloated surface rather than a blisteringly hot one. Because of this, astronomers do not evaluate it the same way they evaluate a blazing blue star. Instead, they use its temperature to determine how much energy each square meter of the star releases. From there, anything brighter than that value must come from having more surface area, meaning a larger radius. The luminosity, temperature, radius relationship comes from a single equation connecting an object's radiated energy to its surface area. Once temperature and luminosity are known, the radius becomes the unknown variable. Temperature can be measured through spectroscopy, and luminosity comes from correcting observed brightness for dust and distance. The radius is simply the value that makes those numbers. Dust extinction complicates this step because it causes the star to appear dimmer and cooler than it truly is. Dust grains absorb and scatter starlight, especially at shorter wavelengths, making the light redder. This reddening has to be undone by comparing the star's colors with the expected spectral signature of an M-type hypergiant. Astronomers apply extinction laws based on how dust typically affects light across different wavelengths. These laws are not guesses. They are grounded in decades of observational research on how interstellar dust absorbs and reflects photons. By measuring how much the star's spectrum has shifted, astronomers can calculate the strength of the dust extinction. Once extinction is quantified, they reconstruct the star's true brightness. For a region like the Stephenson 2 cluster, extinction is extremely heavy, so the corrected luminosity is far higher than the observed value. When Stephenson 218's corrected luminosity is combined with its measured temperature, the radius that emerges is colossal. The final step is confirming the calculation with independent methods. One obvious approach would be to directly image the star's surface. In theory, this would remove the need for assumptions because astronomers could measure its size visually. Unfortunately, this isn't possible. Stephenson 218 is far beyond the reach of direct imaging. Even the most powerful telescopes cannot resolve its disk at its distance. To understand why, consider the angular resolution required. If Stephenson 218 were the size of its actual radius and placed 19,000 light-years away, its apparent size on the sky would be far smaller than 1,000th of an arcsecond. Even extraordinary instruments like the Very Large Telescope Interferometer, VLTI, struggle to resolve red supergiants that are only a few hundred light-years away, and even then the details are blurry. The combination of huge distance and severe dust makes the star's apparent disk far too small for current technology. Astronomers have attempted to simulate what interferometric baselines might achieve using arrays of telescopes working together to create the effect of a giant virtual telescope. The VLTI can combine light from widely spaced mirrors to significantly boost resolution. However, the improvement still isn't enough to distinguish the surface of Stephenson 2. The interferometric baseline would need to be much larger, orders of magnitude larger than anything humanity has built. Simulations show that even with perfect observing conditions, theoretical instruments would struggle because the star's angular diameter remains below the threshold of detection. Light from the star is also distorted by turbulence in Earth's atmosphere, even when adaptive optics are used. And although space-based telescopes avoid atmospheric distortion, no existing space array has the baseline required to resolve a star at that distance. This limitation is not due to the star being faint. Even though dust blocks much of its visible light, Stephenson 2.8, but brightness doesn't help if the star's disk is too small for the telescope to separate from a point source. When a star lies that far away, even a giant hypergiant appears no larger than a pinprick. Despite these imaging limitations, astronomers still have multiple ways to confirm the radius using physical models and high-resolution spectroscopy. Spectral analysis reveals temperature, chemical composition, and atmospheric characteristics. From these, models of red hypergiant atmospheres can be applied to estimate how much energy the star must release at a given temperature to match the observed brightness. When that energy output is compared to the corrected luminosity, the necessary radius falls within the 2000 solar radius range, matching what the first calculations predicted. The consistency among different measurement methods strengthens the case. Distance from Gaia, temperature from spectroscopy, and luminosity from extinction correction all point toward the same conclusion. When independent techniques converge, astronomers gain confidence that the result is real. One of the greatest advantages of modern astronomy is the ability to cross-verify results using different wavelengths. Stephenson 2.18 emits strongly in the infrared, and infrared data offers cleaner measurements of brightness because dust affects infrared light far less. When astronomers compare infrared luminosity with visible light corrected values, the agreement is strong, suggesting that the extinction corrections are reliable and that the star's extreme luminosity isn't an artifact of dust miscalculation. Even though Gaia's direct parallax measurement of the star itself is too noisy to use, the overall cluster distance from Gaia's data is robust enough to anchor the luminosity reliably. The entire cluster's motion and distance solution helped fix Stephenson 2.18's location more accurately than previous surveys. This significantly reduces the uncertainty that plagued early radius estimates. Still, astronomers do account for possible errors because a star this extreme requires caution. They account for alternate extinction curves, uncertainties in dust grain composition along this specific line of sight, spectral classification variations, and temperature uncertainties. Even after adjusting these parameters across reasonable ranges, the star consistently emerges as a hypergiant with a radius in the range of 2. Another important confirmation comes from comparing Stephenson 2.18's luminosity track with established theoretical models of red hypergiant evolution. Stars at this stage of life follow predictable pathways on the Hertzsprung-Russell diagram. When a star reaches a certain luminosity and temperature combination, only one radius range fits the physical laws governing radiative output. Stephenson 2.18 occupies a spot on the diagram that corresponds with stars in the late red hypergiant phase that have expanded near the upper physical limit for a stable stellar envelope. Those models predict remarkably large radii, providing another line of evidence supporting the observational result. Because this star is so far out on the hypergiant evolutionary path, its radius is not surprising within the context of high-mass stellar evolution, but the sheer scale pushes the boundary of what astronomers thought. The result forces astrophysicists to refine their understanding of how large a star's envelope can become before the structure collapses or sheds mass too rapidly to maintain stability. One additional method helps support the radius estimate: variability studies. Red hypergiants often show slow changes in brightness because their outer layers expand and contract. These changes can be tied to the star's physical size and surface behavior. Observing Stephenson 218's variability across multiple wavelengths allows astronomers to reinforce the physical model used to interpret its radius. The star's light curve matches what would be expected from a hypergiant with an exceptionally wide envelope surface gravity. Despite all these methods, direct measurement remains impossible for now to resolve a star as distant and large as Stephenson 218. Astronomers would need either a space-based interferometer with a baseline stretching thousands of kilometers, or a new technology beyond current engineering limits. In the far future, missions capable of linking multiple large telescopes in space could theoretically image stars at these distances. For now, the radius must be derived indirectly, but those indirect methods are powerful when combined. Why red hypergiants can expand to absurd radii. There is a point in stellar evolution where a massive star no longer resembles the compact, tightly bound sphere it once was. A hypergiant reaches this point when its internal structure becomes so stressed and unbalanced that the star essentially swells into a bloated, fragile object whose outer layers barely qualify as material by everyday standards. This inflated form is not an artistic exaggeration. It is the unavoidable end result of physics operating near its limits. A red hypergiant expands because several internal forces push outward with almost no resistance. By the time a star reaches the hypergiant stage, it has burned through much of its original fuel and rearranged its internal layers multiple times. These changes alter how energy moves from the core to the surface, how radiation interacts with gas, and how gravity competes with that outward push. The deeper reason hypergiants reach extreme sizes comes from the combined effects of radiation pressure, changes in opacity, and the structural consequences of losing mass at high rates. The star's core, now burning heavier elements, releases vast energy, and that energy must escape. The layers around the core respond by expanding. Unlike low-mass stars that maintain a stable balance for billions of years, high-mass stars burn so violently that their outer layers cannot stay compact. They balloon outward into a cooler, extended envelope. One of the most important factors is opacity, a measure of how easily photons can move through stellar material. In hypergiants, opacity rises sharply because the gas in the envelope becomes partially ionized or filled with molecules and dust precursors that block radiation. When photons cannot move freely, they build pressure. This pressure pushes the outer layers outward until the material spreads so thin that the radiation can finally escape. In this stage, the star's size is not determined solely by its mass, but by how energy moves through its interior. The envelope expands not because it wants to, but because there is no stable point where it can remain compact. It must become huge simply to let the enormous internal energy leak out. Another driver of extreme expansion is radial instability, which occurs when the star's layers respond slowly or unevenly to changes in pressure. A hypergiant is always on the edge of imbalance. Small internal changes cause large shifts in size. For example, when the opacity in a certain layer increases, it traps more radiation. The pressure rises and the layer expands. When it expands, the temperature drops, the opacity changes again, and the entire structure adjusts. These adjustments are not smooth. They create cycles of expansion and contraction that continually inflate the star. Because the hypergiant is near the end of its life, its core contracts while its outer layers expand. This combination produces a huge low-density envelope where the gravitational pull is weak. The lower the gravity in the outer layers, the easier it becomes for radiation to push them outward. At this point, the star is no longer a compact object, but closer to a swollen shell supported by pressure instead of a strong gravitational grip. There is also the effect of reduced binding energy. As mass is lost through winds and eruptions, the star becomes less able to hold onto its envelope. Gravity weakens as the star loses weight. With less mass pulling inward, the outer layers expand to new equilibrium points. This is why two hypergiants with similar temperatures can have very different sizes depending on how much mass they have already shed. Each of these factors contributes to the dramatic expansion, but together they push the star to the very edge of what a stellar atmosphere can physically maintain. At a certain point, the envelope becomes so extended that it is barely gravitationally bound. The radius grows until the outer layers hover in a region where gravity, pressure, and radiation are almost balanced. In this configuration, the star becomes a diffuse, swollen structure, hundreds or even thousands of times wider than the Sun. Hypergiants remain enormous because nothing stabilizes them. Their envelopes are dominated by unstable energy transport, changing opacity, and relentless mass loss. In this phase, the star is fighting for structural cohesion while shedding material at extreme rates. It is the last stage before the core collapses or the star transitions into a different state. The hypergiant becomes a record breaker because there is no other path for a star of its mass, temperature, and energy out. To release the energy it produces, it must spread out over a colossal surface area. The upper limit of a star's size is set by these same processes. A hypergiant cannot expand indefinitely because the atmosphere eventually becomes too diffuse to remain bound. If the extended layers become so thin that radiation pressure exceeds gravitational pull everywhere, the star loses them entirely. This is why hypergiants often shed material in bursts or eruptions. In many cases, they spend only a short time at their maximum size before losing so much mass that they shrink or collapse into a different phase. Despite their enormous size, hypergiants are fragile. Their envelopes are not thick, solid layers, but enormous volumes of gas, stretched so thin that even small disturbances can eject material. This fragility sets a natural cap on their radius. A star can only expand until its surface layers are on the verge of escape. At that limit, the star's surface becomes a region where gravity barely holds on. If the envelope expands further, it leaves the star entirely. This is why red hypergiants hover near their maximum possible size before shedding mass so rapidly that their overall radius eventually stabilizes or decreases. In short, the largest stars in the universe become large because their internal physics leave them no other option. The expansion of a hypergiant is not a sign of stability, but of a star under stress. The envelope becomes so extended that even a slight imbalance between radiation and gravity ejects matter. In these conditions, The star grows outward until the pressure drops and the density becomes extremely low. At these radii, the star's surface is closer to a boundary between a solid object and a drifting cloud. It remains a star, but only because it still contains a central core producing enough heat to keep the envelope illuminated. Thus, the limit of stellar size is not an arbitrary number. It is the point where the envelope hovers on the threshold between a bound layer and space itself. That boundary defines how large a hypergiant can become before it starts losing more material than it can support. Stephenson 218 sits near this limit, which is why it is considered one of the largest stars ever found. A hypergiant's enormous radius and weak outer gravity lead to one unavoidable consequence: extreme mass loss. Hypergiants shed matter at rates far beyond what most stars experience. For comparison, the Sun loses material steadily through the solar wind, but the amount is tiny, equivalent to a few millionths of Earth's mass per year. A hypergiant, on the other hand, can lose a noticeable fraction of its total mass in a single year. These losses reshape the star's surface, alter its structure, and influence its final fate. Mass loss occurs through several mechanisms operating simultaneously. The most common is steady stellar wind, driven by radiation pressure on atoms, ions, and molecules in the star's outer layers. Because the envelope is so extended and loosely bound, the wind does not require much force to escape. At the temperatures of a red hypergiant, certain molecules absorb photons very efficiently. When they absorb these photons, they gain momentum and push outward. This momentum transfer accelerates gas away from the star and creates a continuous outflow. In hypergiants, this wind can reach speeds of tens of kilometers per second, fast enough to carry enormous amounts of material far from the star. Winds from hypergiants are not uniform. They vary in strength and sometimes become stronger in certain directions. These variations produce arcs, shells, or clumps of material that spread into space. Over time, the star can lose so much mass that its structure changes and the envelope becomes even more unstable. These winds remove both mass and momentum, further weakening the outer layers and allowing them to expand even more. This feedback loop drives the star to its maximum radius and then strips it back down over time. Another source of mass loss is pulsation-driven outflow. The enormous envelope does not stay still. It expands and contracts in slow cycles caused by instabilities in how energy is transported. During contraction phases, the layers heat up and become more opaque. During expansion phases, they cool and become more transparent. These cycles can grow strong enough to lift gas above the escape velocity. When the envelope expands too far, gravity can no longer pull all of the gas back down, so part of it escapes as mass loss. These pulsations can generate large waves on the star's surface that carry matter upward. When the wave crests reach high enough and the density is low enough, the gas breaks free of the star. Hypergiants also lose mass through eruption-like events, although these are less violent than the giant eruptions seen in luminous blue variables. In a hypergiant's case, the eruptions occur because certain regions in the envelope heat up unevenly or because convection cells push material outward too strongly. Where the envelope is thinnest or weakest, the material escapes in large plumes. Over time, these events can carve uneven shapes around the star, forming arcs or shells made of dust and gas. The chemistry of the expelled material helps define what happens to the ejected mass afterward. As the outflow cools, it forms silicates, oxides, and other dust grains. These grains appear in the circumstellar environment around the star and eventually become part of the interstellar medium. Dust from hypergiants is rich in heavy elements because the star has already produced them through fusion. When hypergiants lose mass, they enrich their surroundings with elements such as oxygen, magnesium, silicon, and iron. These elements are essential for forming rocky planets, metal-rich stars, and complex molecules in space. The dust grains in the outflow also influence the mass loss itself. Dust absorbs light extremely well, so radiation can push on dust grains more effectively than on atoms alone. When dust forms, it accelerates the wind further, increasing the mass loss rate. This makes red hypergiants efficient factories of interstellar dust. Even a few 100,000 years of mass loss can create a large dusty region around the star visible in infrared light. Hypergiants do not just lose mass passively. The structure of the envelope encourages mass loss channels. Convection inside the star creates massive cells that reach from deep layers to the surface. These cells carry hot gas upward, cause turbulence, and produce regions where material is ejected more easily. Each cell may be larger than Earth's orbit, meaning the star's outer layers shift and churn on scales that dwarf planetary systems. When a convection cell bursts through the surface, it pushes material outward with significant force. In a hypergiant's thin, weakly bound atmosphere, these convective eruptions accelerate gas beyond the escape velocity. All of this mass loss fundamentally reshapes the hypergiant's life. Losing mass reduces the gravitational pull on the remaining layers, making them even more unstable. In many cases, a hypergiant spends only a short time at its maximum size before mass loss becomes too extreme and begins to shrink the envelope. Once enough mass is lost, the star may transition into a hotter phase, or its core may collapse into a supernova. The exact outcome depends on how much mass remains and how quickly the outer layers disperse. Mass loss also influences the star's environment. As the wind spreads into space, it slows down and cools, forming a circumstellar shell. Over tens of thousands of years, these shells merge with the interstellar medium. The enriched material becomes part of the molecular clouds that will eventually produce new stars. Hypergiants are therefore important contributors to the chemical evolution of galaxies. Their winds carry elements forged in the core of the star and disperse them throughout space. The next generation of stars and planets inherits this material. Because hypergiants are rare and short-lived, each one contributes a large amount of heavy elements in a short time. Their winds help fill the region with dust that can absorb light, form molecules, and eventually act as the seeds of new planetary systems. When one hypergiant dies, the region around it becomes richer in elements that would not exist without its mass loss process. The mass that hypergiants lose can also interact with the winds and radiation from neighboring stars. In clusters like Stephenson 2, where multiple massive stars evolve at the same time, the combined winds shape the interstellar medium into cavities, bubbles, and compressed regions. These interactions may trigger new star formation or clear out large spaces in the cluster. The expelled dust and gas from a hypergiant often become part of these larger structures. Hypergiants leave a legacy not only through their final explosion, but through the material they shed long before they die. The dust grains and molecules in their winds end up in places far from where the star originally formed. Over millions of years, this material becomes part of new systems, that inherit the elements synthesized deep inside the hypergiant's core. In this sense, the hypergiant's mass loss process is one of the most important contributions it makes to the galaxy. Hypergiants lose mass because their enormous size stretches their structure to the limit. Radiation pressure, high opacity, weak gravity, and turbulence all work together to unbind the outer layers. The star cannot remain stable, so it sheds material at extreme rates. These processes define how large a hypergiant can become and how long it can stay that large. As soon as the envelope grows too extended, mass loss increases and the star begins to shrink again. The limits of stellar size and the mechanisms of mass loss are tightly connected. A hypergiant grows until the outer layers rest at the boundary, where radiation pressure nearly overcomes gravity. At that point, the star becomes huge, bright, and fragile. With every eruption or strong wind, the envelope loses material and the star readjusts. This cycle continues until the core reaches the end of its fusion stages. When that happens, the star no longer supports the envelope. Gravity takes over and the core collapses. The hypergiant's life ends abruptly, but its material continues to shape space long after the star is gone. What happens when Stephenson 218 dies? A star as large as Stephenson 218 is not built for a quiet ending. It has been burning through its nuclear fuel at a pace far beyond what smaller stars can ever achieve, and as a result, it is forced toward a violent conclusion. Its enormous size, weak outer gravity, unstable envelope, and advanced internal fusion stages all point toward the same outcome. It will end in a core collapse, supernova. Nothing else can tear apart a hypergiant of this mass. Nothing else can shut down the crushing weight at its center once the nuclear reactions stop. When Stephenson 218 reaches the end of its fuel supply, its death will be a major event for its region of the Milky Way. It will reshape the environment of the Stephenson 2 cluster and leave a long-lasting mark that will be detectable far into the future. The path to the supernova begins deep inside the star, where its core has already gone through most of the elements that massive stars burn: hydrogen, helium, carbon, and likely oxygen and neon. Each stage pushes the star closer to collapse. The heavier the nuclei involved in fusion, the shorter the burning stage becomes. While hydrogen burning lasts millions of years, and helium burning lasts hundreds of thousands, later stages burn out rapidly. Neon, oxygen, and silicon burning last only years, months, or even days. Once the star reaches iron in its core, the result is predetermined because iron cannot be fused into heavier elements without consuming more energy than the process produces. At that point, the core no longer generates enough outward pressure to resist gravity. The collapse becomes unstoppable. When the core collapses, the entire internal structure of the star reacts in a brief, violent moment. Gravity pulls the core inward faster than anything in the outer layers can respond. The collapse accelerates until the core slams into densities similar to those of atomic nuclei. Electrons and protons merge into neutrons. Neutrinos burst out almost instantly. The core becomes so stiff that it cannot shrink further. The sudden halt of collapse triggers a rebound shockwave. That shockwave, powered by a massive outpouring of neutrinos and the collapse energy itself, travels outward at extraordinary speed. As it pushes through the star's material, the shock heats the gas to temperatures so high that new elements form in fractions of a second. These elements are blasted outward and become part of the galaxy. This is the beginning of the supernova. Stephenson 218 is almost certain to produce a Type 2 supernova, the kind associated with massive stars that retain hydrogen in their outer layers. Even though it is losing mass constantly through its hypergiant winds, it still holds on to a huge reservoir of hydrogen. Type 2 supernovae occur when the star's outer layers collapse inward and then explode outward after the core collapses. Because Stephenson 218 has such a large hydrogen envelope, its supernova will be prolonged compared to explosions from stars that have lost most of their outer layers. The shock wave will take more time to move through such an extended envelope. This produces a characteristic brightness pattern, a rapid rise in luminosity followed by an extended plateau where the light remains nearly constant for weeks or months before it declines. The size of the star's envelope will shape the supernova's early appearance. Stephenson 218 is roughly 2,000 times the radius of the Sun, and this vast size means the shock wave has a long distance to climb before the explosion becomes visible. When the shock reaches the surface, the sudden release of radiation produces an event known as shock breakout. For a star this large, the shock breakout will produce a flash of light across ultraviolet and visible wavelength, and a rapid heating of the outer layers. Because those layers are thin and diffuse, the shock breakout may not be as intense as in more compact stars, but it will be broad and extremely bright. Once the shock clears the surface, the entire envelope begins expanding outward at thousands of kilometers per second. After the shock breakout, the supernova enters its main luminous phase. In Type 2 supernovae from red supergiants, the brightness reaches many billions of times the luminosity of the Sun. Even from a distance of 19,000 light-years, Stephenson 218's explosion will stand out. It will become one of the brightest objects in that region of the Milky Way, easily detectable by modern telescopes and possibly visible to the naked eye from dark locations on Earth as a faint point of light. It will not be bright enough to cast shadows or overpower the moon, but for astronomers it will be a remarkable and rare event. A massive hypergiant supernova in our own galaxy is something modern science has not yet witnessed up close. The energy released in the explosion will be enormous. The supernova's shock wave will travel outward at thousands of kilometers per second, sweeping through the surrounding material in the Stephenson 2 cluster. Because this cluster contains many other massive stars, the combined radiation, winds, and past supernova remnants will interact with the new shock wave. The region will become a complex environment where high-energy particles, shock-heated gas, and enriched material mix together. The shock wave will eventually slow down as it picks up material, compressing and heating the interstellar medium around the star. Over tens of thousands of years, it will create a supernova remnant, a large expanding cloud of gas filled with heavy elements that will continue to grow until it disperses into the surrounding space. One of the most significant questions is what happens to the core of Stephenson 218 after the explosion. Massive stars can leave behind neutron stars or black holes depending on their mass structure and the exact details of their collapse. In Stephenson 218's case, the core is almost certain to collapse directly into a black hole. The star is simply too massive to produce a stable neutron star. For a neutron star to form, the collapsing core must settle into a state where neutron degeneracy pressure counteracts gravity. But in extremely massive stars, the mass of the core exceeds the limit where this is possible. The collapse continues until the core forms a black hole. Direct collapse into a black hole can take two forms. In one scenario, the core collapses into a black hole, but still launches a strong outward shock that produces a full, bright supernova. This is the expected outcome for Stephenson 218 because the outer envelope is massive enough to absorb and radiate the energy of the initial explosion. In the second scenario, the collapse leads to a weak or failed supernova, where much of the star falls directly into the black hole with minimal luminosity. This is unlikely for a star with such a large hydrogen envelope. The shock will almost certainly generate a visible supernova before the envelope begins falling inward or dispersing. Thus, the most probable outcome is a bright Type II supernova, followed by the formation of a black hole. The brightness of the supernova will depend on the details of the explosion, the energy of the shock wave, and the amount of material the shock interacts with. Most Type II supernovae reach absolute magnitudes around 1/17, with some reaching from Earth's distance of 19,000 light-years. A supernova of that brightness would appear between magnitude pi6 and Fendy. This means that under dark skies away from city lights, the supernova might appear as a faint star visible to the naked eye. With binoculars or small telescopes, it would be clearly visible. Professional observatories would be able to follow the event in detail, capturing the rise, plateau, and decline of its light curve. The explosion would become one of the most closely studied events in modern astrophysics. The shock wave from the supernova will expand outward into the cluster at tremendous speed. The initial shock may travel at more than 10,000 kilometers before it begins slowing down. As it sweeps through the surrounding space, the shock compresses any gas it encounters. These compressed regions can later trigger new star formation as the material cools and collapses under gravity. In many cases, supernovae act as the final push that turns unstable gas into newborn stars. Stephenson 218 supernova could spark new generations of stars in its region of the Scutum-Centaurus arm. This is one reason massive clusters like Stephenson 2 can sustain star formation over extended periods. Their most massive stars produce winds, radiation, and supernova shock waves that constantly reshape the environment. The explosion will also distribute heavy elements throughout the cluster. The fusion processes inside the star and during the supernova will create elements such as silicon, sulfur, calcium, and iron. These elements are essential building blocks for planets, rocky bodies, and complex molecules. The material ejected by the supernova will enrich the interstellar medium, making future stars in that region richer in metals. Over long time scales, this contributes to the chemical evolution of the galaxy. Massive stars like Stephenson 218 help seed space with the elements that become part of planets like Earth. Because the supernova will happen at a great distance, it poses no threat to life on Earth. Even the brightest part of the explosion will be far too faint to cause any harmful effects. At 19,000 light-years, the energy reaching Earth will be negligible. High-energy radiation from the supernova, including gamma rays, X-rays, and cosmic rays, will be absorbed or scattered long before they reach our solar system. Only supernovae within a few dozen light-years pose a potential hazard to Earth's biosphere, and Stephenson 218 is hundreds of times farther away than that threshold for Earth. The explosion will be a fascinating astronomical event, not a danger. Despite its safety, the event will leave a clear mark across the Milky Way. A supernova of this scale will illuminate dust and gas in the region creating glowing filaments and arcs that will be visible in infrared and radio wavelengths for thousands of years. As the shock wave expands, it may create a supernova remnant comparable in size. Well-known examples like the Crab Nebula, although the shape and structure will depend on the density and distribution of gas in the region. Over time, the remnant will continue expanding until it blends with the surrounding interstellar medium. Astronomers will use radio telescopes, infrared observatories, and spectroscopic surveys to map PAT's growth and analyze the heavy elements within it. A supernova like this also produces a burst of neutrinos that travel through space almost unimpeded. When the explosion finally reaches Earth's line of sight, neutrino observatories will detect a burst lasting only a few seconds, but containing an enormous number of neutrinos. This burst will provide direct information about the core collapse, including the behavior of matter at extreme densities. Neutrino detections from supernovae are rare, and capturing data from one in our own galaxy would be a major scientific achievement. Even before the visible light arrives, neutrino detectors would announce the event, giving astronomers a chance to prepare telescopes for the optical, ultraviolet, and infrared phases. When the core collapses into a black hole, it will leave behind an object with several times the mass of the Sun. This new black hole will be surrounded by expanding ejecta from the explosion. Over time, the black hole may interact with nearby material, but in many cases, black holes left by isolated stars remain relatively quiet. Without a companion star or significant nearby gas, they become nearly invisible, detected only by their gravitational influence. The remnant of Stephenson 218 will likely fade into obscurity within the cluster, hidden among the background stars and dust. However, its supernova remnant will remain visible for ages. The end of Stephenson 218 will also affect the structure of the Stephenson 2 cluster. As one of the largest and most luminous members, its death will reduce the overall brightness of the cluster. It will also redistribute material that can support new star formation. The shock wave from the explosion will compress nearby gas, and the enriched ejecta will seed the region with heavy elements. Over long periods, the cluster will evolve as new stars form, old stars die, and the cluster gradually disperses. The supernova will mark a key moment in that evolution. While the timeline for Stephenson 218's death is uncertain, it is likely to occur within the next 100,000 years or less. For a star this massive and evolved, this is the final stretch. It will not survive long in astronomical terms. When it does explode, it will become one of the most important astronomical events observable from Earth in our era. Modern instruments will capture data across multiple wavelengths, building a complete record of the life and death of one of the galaxy's largest stars. The final moments of the star will play out quickly from the star's perspective. Once the core reaches the iron stage, collapse will occur in less than a second. The shock wave will form and race outward. The neutrino burst will pass through the star and through space toward Earth. Minutes later, the shock will reach the surface. The outer layers will tear apart and begin expanding into space. Light from the explosion will travel for 19,000 years before reaching Earth. When that light arrives, the event will already have happened long ago from the star's point of view. Stephenson 218's supernova will be a key target for theorists and observers. Massive red hypergiants like this are rare and their explosions provide insight into the upper limits of stellar evolution. The data from such an event will help refine models of core collapse, neutrino processes, shock propagation, and heavy element formation. Because red hypergiants have enormous envelopes, they produce different explosion signatures compared to compact blue supergiants or stripped envelope stars. The extended plateau phase of the light curve will allow astronomers to study how shock waves interact with massive hydrogen envelopes. This will help distinguish between different supernova mechanisms and allow scientists to understand how hypergiants contribute to galactic chemistry. The legacy of Stephenson 218 will continue long after its light fades. The elements forged in its core will spread into space. The supernova remnant will grow and evolve. The black hole at its center will remain hidden. The enriched gas will become part of new generations of stars. Its death will not be an end, but the beginning of many other processes. In this way, the star will shape its environment long after it disappears from view. The death of Stephenson 218 will be dramatic, powerful, and scientifically valuable. It will reveal how extreme stars end their lives and how much energy they release in their final moments. It will confirm the fate of massive hypergiants and help refine the boundaries between neutron star and black hole formation. And it will show once again how stars contribute to the structure and evolution of the galaxy. From Earth's perspective, the event will be spectacular, but safe. 19,000 light-years place it far outside any hazardous range. Its light will arrive as a historic event for astronomy. Telescopes across the planet and in orbit will turn toward the Scutum Centaurus arm. Data will pour in across every wavelength. The explosion will become one of the best studied supernovae in our entire catalog. Stephenson 218 is nearing the end of its life, but its death will be one of the richest scientific moments ever produced by a single star in our galaxy. It stands on the edge of collapse, supported only by the last remaining stages of fusion. When those reactions stop, the star will fall inward, the shock will rise, and a supernova will reshape its surrounding. Its long life as a hypergiant will give way to a final flash of energy that will carry its material outward across the Milky Way. The explosion will be the last chapter of one of the largest stars ever discovered, and the beginning of many others that form in its wake. Stephenson 218's claim as the largest known star in the Milky Way is powerful, but it is not without controversy. In the scientific community, particularly among stellar astrophysicists, its size, luminosity, and even its membership in the Stephenson 2 cluster remain subjects of debate. These debates hinge on multiple layers of uncertainty: how well astronomers can correct for dust extinction, how precisely they know its distance, how it compares to other candidate giants, and whether future observations will force a major revision of its estimated radius. Uncertainties in dust extinction models. One of the most challenging problems when measuring Stephenson 218's properties is the thick dust between us and the star. This dust absorbs and scatters light, especially at optical wavelengths, and distorts the star's observed colors. Correcting for this effect, what astronomers call dust extinction, or reddening, is not straightforward. Different extinction models can yield significantly different results in luminosity and, by extension, in extinction is described by so-called extinction laws, which tell how much light is absorbed per unit distance, depending on the wavelength. But the problem is that not all dust is the same. Dust grain sizes, composition, and spatial distribution change from one part of the galaxy to another. In a region as dense and complex as the Scutum Centaurus arm, where Stephenson 2 lies, dust properties may differ substantially from the average models used by many astronomers. Some early studies of Stephenson 2 assumed a very high extinction along the line of sight, based on broad brush models. Others argued that part of the reddening could originate from circumstellar dust, the dust ejected by the red supergiants themselves, forming local shells or envelopes around each star. If some of the observed extinction is actually local to Stephenson 218 rather than interstellar, then correcting using only interstellar extinction laws will overestimate its true luminosity. A key study by Davies in a draft paper revisited this problem and reevaluated the average extinction for the cluster. They recalculated the extinction parameter by excluding some stars in the cluster that showed unusually high redness, arguing that these might be influenced by individual circumstellar dust, not just the interstellar. By doing this, they obtained a lower mean extinction in their infrared band and clarified the uncertainty in how much light was being blocked. But even with these refined values, they still adopted a 10% error on luminosity simply due to remaining uncertainty in the extinction. The fact that different teams adopt different extinction corrections reflects how unsettled this issue is. Some models may undercorrect, making the star seem dimmer than it truly is. Other models might overcorrect, artificially inflating the luminosity. Small shifts in the extinction estimate propagate into large shifts in radius because of how the Stefan-Boltzmann relation ties together luminosity, temperature, and radius. This uncertainty is not specific to Stephenson. It affects almost all highly reddened hypergiants, especially in dense, dusty regions of the galaxy. As a result, debates over whether we have over- or underestimated Stephenson 218's size remain central in the literature. Distance is the foundation upon which size estimates rest. If a star is farther than assumed, its true luminosity is higher. If it's closer, the luminosity is lower. For Stephenson 2, there remains a debate over just how far it is, and different studies report slightly different values. Some place the cluster around 5.8 kiloparsecs, kpc, while others suggest it could be as far as 6.0 kpc or more. That may sound like a small difference, but it translates into meaningful variation in calculated physical parameters. One of the earlier kinematic distance measurements, based on the motion of stars in Stephenson 2 and the velocity of gas in the same region, gave a distance of 6 kpc. At the same time, some teams working with extinction-corrected photometry favor a distance slightly above 6 kp. These differences might seem subtle, but when plugged into luminosity calculations, they represent an uncertainty of tens of percent in brightness. The arrival of Gaia data further sharpened, but did not fully resolve the issue. Gaia Data Release 2, DR2, and Data Release 3, DR3, provided much more precise parallax measurements for many cluster stars. However, Stephenson 218 itself is heavily reddened and faint in Gaia's optical bands, which makes its parallax measurement noisy and uncertain. So astronomers rely on combining Gaia data from many cluster members rather than just the hypergiant itself. These average distances suggest a value close to 5.8, 6.0 kpc, with reduced uncertainties compared to older kinematic methods. But they do not eliminate the debate completely, because the distance range remains broad. Some critics argue that the radius of Stephenson 218 may not be as large as its most optimistic estimates. If the cluster is actually closer, the luminosity and therefore radius would be lower. Conversely, if the cluster is slightly farther, the size could be even more enormous. This wiggle room keeps some astrophysicists cautious about declaring it definitively the largest star. Stephenson 218 is a strong candidate for the title of largest known star, but it is not the only one that is claimed at various times to be the most massive or most extended. Several other red supergiants and hypergiants remain in the conversation, and comparing them highlights both the difficulty and fluidity of largest star claims. G64, located in the Large Magellanic Cloud LMC, was once widely cited as the largest star. In a paper by Levesque, Massey, Plez, and Olson, astronomers used modeling of its dusty environment to estimate its radius at around 1540 solar radii. That size is extreme, and for a long time G64 was considered a top contender for the largest known star. Its outer shell of circumstellar dust, massier activity, and molecular features made it a particularly exotic object. And because it's in a different galaxy, their measurements came with somewhat different modeling challenges. Viconis Majoris is another famous giant, with past estimates placing its radius at about 1,200 solar radii. It remained among the largest known galactic red supergiants for decades, but even this legendary star's size has evolved as models improved. Different measurement techniques and assumptions about distance, temperature, and structure have revised some of its earlier extremes downward. There are other candidates as well. The hypergiant W-Cephei, for instance, has been studied with powerful interferometric instruments. It shows dramatic variability and structural asymmetry, and its radius has been estimated at well over 1,000 solar radii. Such stars illustrate how complicated this field is. Each largest star claim depends profoundly on the methods, models, and data behind it. In lists of the largest known stars, Stephenson 218 often sits at the top, but those lists evolve as new measurements come in, as instrumentation improves, and as theoretical models get refined. The existence of other extreme candidates means that even if Stephenson 218 holds the top spot now, future revisions may change that for better or worse. Despite the debates, many astronomers favor Stephenson 218 as the current record holder for biggest known star. Why? Several converging lines of evidence support its extreme size, and no competing candidate currently matches it on odd key metrics under the same level of scrutiny. First, the luminosity is exceptionally high. Even after applying conservative extinction corrections, its bolometric luminosity is estimated around 440,000 times the Sun. That is significantly more luminous than many other large red supergiants, especially when combined with its low surface temperature, approximately 3,200 K. This combination, low temperature plus huge luminosity, essentially forces a very large radius when placed into stellar models. Second, the spectral type M6 is unusually late for a supergiant. This is not a trivial classification. A spectral type of M6 implies a very cool surface temperature, which in turn demands a large diffuse photosphere to produce the observed energy output that expands the inferred radius further. Third, the cluster membership strengthens the case. Because Stephenson 218 resides in a well-studied red supergiant cluster, Stephenson 2, its distance and evolutionary context are more reliable than if it were an isolated field star. The cluster's distance, as refined by Gaia and kinematic models, reduces the uncertainty in the radius calculation. The fact that it is part of a synchronized group of massive stars with similar ages and similar extinction environments helps reduce systematic errors that might affect single star analyses. Fourth, the consistency across independent methods adds confidence. Multiple teams have looked at Stephenson 2 at 18 using different datasets, infrared SED fitting, spectroscopy, cluster distance modeling, and still converge to very large radii. While no method is perfect, the agreement among them suggests that the extreme size is not just an artifact of one technique gone wrong. Finally, theoretical stellar evolution models support a star of Stephenson 2 at 18's mass and age reaching such inflated sizes. Models of very massive red supergiants show that, under the right conditions, high luminosity, extended envelope, high mass loss rate, a hypergiant envelope can stretch to thousands of solar radii while remaining borderline gravitationally bound. Stephenson 2 at 18 aligns with that theoretical regime in a way that few other known stars convincingly do. In recent years, several studies have contributed to refining our understanding of Stephenson 218. While a full literature review is beyond this chapter's scope, a few notable developments stand out. In a revised cluster study, astronomers reanalyzed photometry and infrared data for many red supergiants in Stephenson 2. They recalculated extinction values, particularly in the near-infrared, to exclude stars likely contaminated by their own circumstellar dust. This lowered the assumed average extinction, and hence the corrections applied to luminosity for key members like Stephenson. Other teams used the Anders, Kalatian, and Stephenson distance extinction model applied to Gaia DR2 stars and cross-matched with infrared catalogs to improve distance and extinction estimates across dust-heavy regions. This model is sophisticated and accounts for varied stellar parameters, helping reduce systematic errors in both distance and brightness. Spectroscopic analyses, infrared and optical, have continued refining the spectral type, effective temperature, and atmospheric models for Stephenson 218. These help reduce uncertainties in the black body-like calculations used to derive its radius. Simulation work and theoretical modeling have explored how dust shells, mass loss rates, and wind behavior alter a hypergiant's apparent brightness and structure, allowing more realistic fits for the star's observed spectral energy distribution. While not all these papers agree on every value, the trend has been toward more careful modeling and more robust constraints on the parameters that define Stephenson 218's size. These refinements strengthen its status as possibly the largest star known, even while admitting uncertainties. Infrared astronomy remains central to studying Stephenson 218 and similar hypergiants because the dust that conceals these stars in visible light is far more transparent to infrared. Several infrared surveys and observatories have provided critical data. Large-scale surveys like 2MASS, WISE, and Spitzer have mapped the regions containing the Stephenson 2 cluster, giving photometric measurements in multiple infrared bands. These data help reconstruct the star's spectral energy distribution, SED, across a wide range of wavelengths, critical for estimating its bolometric luminosity. More recently, ground-based infrared telescopes equipped with sensitive spectrographs have targeted members of the Stephenson 2 cluster to measure spectral types, atmospheric properties, and mass loss indicators, for example, molecular features, dust emission. Space telescopes, such as Spitzer, in its later phases, and other infrared missions, have helped map the dust environment around the cluster, helping refine extinction values more precisely than earlier, cruder dust models allow. These ongoing observations contribute to a dynamic, evolving picture of Stephenson 2. Astronomers continue to update the SED, monitor variability, and test how much dust is local versus interstellar. All efforts to reduce the biggest sources of error. The biggest hopes for resolving standing debates around Stephenson 218 rest with upcoming and recently deployed advanced telescopes. Instruments like the James Webb Space Telescope, JWST, and future extremely large ground telescopes like the European Extremely Large Telescope, ELT, offer exciting because JWST operates in the infrared and mid-infrared. It is ideally suited to peer through dense dust and characterize the SE of Stephenson 218 more precisely than ever before. With its superior sensitivity and spectral resolution, JWST could better separate the star's light from surrounding dust emission, identify dust shell features, and refine estimates of its effective temperature, luminosity, and extinction. Crucially, JWST may detect and resolve circumstellar dust structures, which would help determine how much of the reddening is interstellar versus local to the star. The ELT, Extremely Large Telescope, when operational, will have a primary mirror spanning tens of meters, giving it unprecedented resolution and light-gathering power. While directly imaging the disk of Stephenson 218 remains beyond reach, the ELT may be capable of interferometric or astrometric techniques to better constrain its angular size, measure Murmas variations, or detect asymmetries in its envelope. With sufficiently long baselines, large ground arrays might begin to approach the angular resolution needed to resolve the outer structure of very distant red hypergiant. Next-generation interferometers, missions, or facilities that might link multiple large telescopes in space or on Earth could push angular resolution for future instruments, could potentially resolve the outer envelope of Stephenson 218, detect its asymmetries, or directly measure structural features that today rely only on models. If such an interferometer ever becomes viable, it could provide a direct test of radius estimates derived from indirect methods. Upcoming time domain missions, including ground-based ones, will constantly monitor the brightness of variable stars across multiple wavelengths. For Stephenson 218, this means tracking its long-term light curve, pulsations, and eruptive mass loss events in unprecedented detail. Better temporal coverage could clarify how much of its brightness changes result from dust, pulsation, or wind, rather than structural size shifts. That will help disentangle which radius models are physically plausible. These new observations will contribute not just to confirming Stephenson 218's size, but to understanding how hypergiants behave, evolve, and interact with their environments at the extremes of stellar physics. At its core, the debate over Stephenson 218's size is not simply about bragging rights. It is a test of how well astrophysics can measure and understand the universe's most extreme stars. The key points of contention: dust extinction, distance, and competing giant star cadence are not petty disagreements, but reflect how difficult it is to study luminous, distant, dust-shrouded objects. If Stephenson 218 really is as large as many of the current models suggest, it challenges the theoretical limits of how big a star can become while remaining marginally bound. It pushes models of convection, mass loss, and radiation transport to their extremes. If future observations reduce its size drastically, that too would be significant. It would suggest earlier models overestimated either the distance, the extinction, or both, and would force a reevaluation of how we calibrate and trust measurements for other distant hypergiants. The ongoing debate also shows how essential advanced infrared and high-resolution telescopes are for other dusty regions of the galaxy. Stephenson 218 is not unique. There may be more giant stars lurking in other clusters behind dense dust. Stephenson 218 stands at the center of an active and ongoing scenic debate. While its current size and luminosity estimates place it as the largest known star, those values rely on extrapolations built over heavy dust, uncertain distances, and complex modeling. Competing giants like WUG 64 and VY Canis Majoris still contend for prominence, but at present Stephenson 218 remains the strongest candidate, supported by multiple independent lines of evidence and refined by modern survey data. Even so, the margin of error is significant, and the biggest questions remain open. Uncertainties in extinction models, cluster distance, and competing stellar geometries all leave room for revision. The confirmation or refutation of its radius will likely come from the next generation of telescopes, JWST, ELT, space-based interferometers, and dedicated variability surveys. Whatever the final number turns out to be, the debate over Stephenson 218 is more than a race for biggest star. It is a frontline exploration of stellar physics, telling us how matter behaves under extreme pressure, how radiation shapes atmospheres, and how the universe recycles its most massive creations into the next generations of stars and planets. Stephenson 218 exposes stellar evolution under extreme conditions. While textbooks present a neat sequence, hydrogen burning, helium burning, red giant expansion, supernova collapse, Stephenson 218 challenges these simplifications. Its radius, estimated between 2,050 and 2,500 times that of the Sun, its temperature hovering around 3,200 Kelvin, and its luminosity near 440,000 solar units, place it in a rarefied category. Most stars do not survive in this regime. They are unstable, subject to intense pulsations, extreme convection, and catastrophic mass loss. By observing these instabilities, astronomers can see real-time evidence of the physical processes that theoretical models predict, but rarely allowed to be tested in isolation. The combination of enormous size and low surface gravity provides a natural laboratory for studying how radiation pressure interacts with massive, tenuous stellar envelopes. Nuclear physics is another area where Stephenson 218 exerts its influence. The star's core has burned through hydrogen long ago and is believed to be in the late stages of helium or carbon fusion. These nuclear reactions, occurring under immense pressure and temperature, define not only the star's luminosity, but also its lifetime. By measuring surface properties such as pulsation period, mass loss rate, and temperature, scientists can indirectly infer the internal reaction rates. Variations in these observable quantities test models of nuclear fusion under conditions far beyond the Sun's relatively stable core. In effect, the star is a natural experiment, validating or challenging calculations of fusion cross-sections, convective overshoot, and energy transport mechanisms that are otherwise impossible to recreate in laboratories on Earth. Stephenson 218 also feeds the galaxy with heavy elements, functioning as a stellar forge for the cosmos. Red hypergiants are among the primary contributors to the enrichment of the interstellar medium. Through winds that can reach tens of kilometers per second, the star sheds material loaded with newly formed elements, including oxygen, silicon, and heavier metals forged in its core. While its outer layers are extremely diffuse, the cumulative effect over millions of years is significant, creating a reservoir of chemically enriched gas that will seed future generations of stars and planets. Observing the composition and distribution of this expelled material allows astrophysicists to quantify stellar yields, the amount of each element produced by a single star. These measurements inform models of galactic chemical evolution, helping scientists understand why some regions of the Milky Way are richer in heavy elements than others. Although Stephenson 218 may not yet have a visible nebula, the principles it demonstrates are central to nebula formation. Hypergiants generate extended envelopes through mass loss, and when a star like this eventually explodes as a supernova, the kinetic energy interacts with surrounding material to create luminous nebulae. Even before that final collapse, the expelled gas and dust help sculpt the local interstellar medium. Winds from Stephenson 218 can collide with outflows from neighboring red supergiants, creating shocks, cavities, and filamentary structure. These interactions contribute to the patchwork of dense and rarefied regions in the spiral arm, influencing where and when the next generation of stars can form. In this sense, the star is not merely a passive participant, but an architect of its cosmic neighborhood, shaping the density and composition of the gas clouds around it. One of the more subtle but profound contributions of Stephenson 218 is its role in seeding heavy elements beyond the immediate vicinity. Massive stars like this create the building blocks for rocky planets and biologically important molecules. While the star itself is destined to end in a Type II supernova, the material it expels through winds prior to that event already carries metals outward, distributing them across parsecs of space. In the long term, this contributes to galactic metallicity gradients, explaining why inner regions of galaxies often show higher concentrations of heavy elements than the outskirts. Each expelled atom of oxygen, carbon, silicon, or iron from Stephenson 218 represents a contribution to the cycle of matter that will one day be incorporated into new stars, planetary systems, and potentially habitable worlds. The extreme nature of Stephenson 218 also tests the limits of physical laws as applied to stars. Its radius, mass, and temperature combinations challenge assumptions about hydrostatic equilibrium and radiative transfer. The star's outer layers are so extended and tenuous that gravity and pressure are finely balanced, meaning that small variations in energy output or opacity can produce dramatic expansions, contractions, or instabilities. Studying these effects gives astrophysicists benchmarks for the behavior of the largest possible stars and refines the theoretical limits of stellar structure. For example, models of radiation pressure on extended envelopes can be calibrated using data from Stephenson 218, allowing predictions about whether a hypergiant of a given mass can sustain its atmosphere or will shed it rapidly in eruptive events. The star's extreme properties also define what stars can and cannot be. By pushing against the upper size limits of stellar evolution, Stephenson 218 clarifies the boundary between ordinary red supergiants and hypergiants, between stable nuclear burning and inevitable collapse. It is a tangible example of the constraints imposed by physics, the maximum radius a star can reach without shedding its outer layers entirely, the maximum luminosity sustainable without becoming gravitationally unbound, and the interplay between convection and mass loss that dictates its surface behavior. Every observation acts as a constraint, narrowing the range of physically plausible models and informing simulations for both Milky Way stars and extragalactic hypergiants. Beyond the Milky Way, studying Stephenson 218 informs our understanding of population 3 stars, the first generation of stars in the universe. These primordial stars formed from gas consisting almost entirely of hydrogen and helium, lacking the metals we see today. While Stephenson 218 is far more metal-rich than Population 3 stars, its extreme size, high luminosity, and instability provide a practical analog. The first stars were expected to reach similarly massive radii and luminosities, producing enormous winds and explosive ends that enriched the early universe with metals for the first time. Observing how Stephenson 218 behaves allows astrophysicists to test models of stellar structure and evolution in a regime that approximates the physical conditions of those ancient giants. In a sense, it is a bridge linking local observable hypergiants with theoretical constructs that shaped the cosmos billions of years ago. Stephenson 218 also demonstrates the interconnectedness of stars and galactic structures. Hypergiants like it contribute to the shaping of spiral arms, not through gravity alone, but by regulating the distribution and compression of gas. The cumulative effect of winds, mass ejections, and eventual supernova explosions from multiple massive stars helps maintain the density contrast necessary for spiral structure and ongoing star formation. In clusters like Stephenson 2, the combined influence of multiple red supergiants can be mapped, and Stephenson 218's extreme properties act as the most dramatic case study. Observing how its energy output interacts with surrounding clouds informs models of galactic dynamics, showing how individual stars can leave an imprint on structures spanning thousands of light years. Studying Stephenson 218 also gives insights into stellar life cycles and feedback loops. The star's mass loss, pulsation, and eventual supernova event feed energy and momentum into the interstellar medium, triggering shock waves that compress neighboring clouds and potentially initiate star formation. Each of these processes can be observed, modeled, and quantified, making Stephenson 218 a crucial reference point. Its immense luminosity and low surface gravity allows scientists to observe phenomena that would be too subtle in smaller stars, such as the formation of asymmetric envelopes, dust condensation in extended atmospheres, and interactions with local magnetic fields. The star's radius and temperature extremes allow for testing of opacities and convection in ways impossible with smaller stars. Its envelope is so extended that photons can be trapped, scattered, or reabsorbed multiple times before escaping, providing a natural laboratory for radiative transfer models. Observations of how light is emitted, absorbed, and redistributed across its photosphere give empirical constraints for computational models. Similarly, the sheer size allows the study of enormous convection cells which can span hundreds of millions of kilometers, giving direct evidence for mechanisms that in smaller stars occur at scales impossible to resolve. Finally, Stephenson 218 is valuable for refining stellar population synthesis models. Its extreme characteristics serve as a benchmark for calibrating the upper ends of the mass and size functions used in simulations of galaxy evolution. By understanding the limits and behavior of the largest stars, scientists can better predict the integrated light of stellar populations in distant galaxies, model feedback processes in galaxy formation, and understand the chemical evolution of the cosmos over time. Observations of its mass loss, luminosity, and pulsations feed into these models, offering a concrete reference that theoretical approximations cannot match. The